Space beckons with its myriad mysteries, challenging our understanding and igniting our imagination. From the enigmatic depths of black holes to the puzzling behavior of distant galaxies, the cosmos is rife with phenomena that defy easy explanation. Join us as we unravel the secrets of the universe, one cosmic riddle at a time. Beneath the thick and toxic clouds of Venus lies an incredibly hostile environment that is far from welcoming to any form of life as we know it. The atmosphere of Venus is primarily composed of carbon dioxide, with clouds of sulfuric acid casting a shroud over the planet. These clouds create a greenhouse effect so intense that surface temperatures average around 800 degrees Fahrenheit, making it hotter than the surface of Mercury, despite being further from the Sun. The atmospheric pressure on Venus is another critical factor contributing to its inhospitable nature. At the surface, the pressure is approximately 90 times that of Earth, akin to being nearly a mile beneath the ocean. This immense pressure would crush any human-made spacecraft, making exploration extraordinarily challenging. The combination of extreme temperature and high pressure creates conditions that are far beyond what any known organism on Earth could endure. Additionally, the surface of Venus is marked by volcanic activity, which contributes to its severe landscape. Scientists believe that many of these volcanoes may still be active, releasing additional gases and contributing to the planet's already thick atmosphere. The presence of volcanic plains and vast highland areas adds to the intrigue of Venus, revealing a planet shaped by powerful geological forces. In recent years, scientists have even speculated about the potential for microbial life in the upper layers of the atmosphere, where conditions are slightly less extreme. However, the harsh environment on the surface, combined with the presence of sulfuric acid clouds, makes Venus largely uninhabitable for any complex life forms. The secrets hidden beneath its clouds continue to fascinate researchers, thus sparking ongoing missions to study this enigmatic planet further. The idea of a ninth planet lurking in the distant reaches of our solar system has gained traction among astronomers in recent years, primarily due to the unusual orbits of certain celestial objects in the Kuiper belt. These distant, icy bodies exhibit gravitational influences that suggest the presence of an unseen giant planet. This hypothetical planet is often referred to as Planet 9, or sometimes Planet X, though no direct observations of it have been made yet. Planet 9 is believed to be significantly larger than Earth, possibly several times its mass, and to have a highly elliptical orbit that takes it far beyond the known planets. Some models suggest it could be located anywhere from 20 to 800 astronomical units from the Sun, where 1 astronomical unit is the average distance from Earth to the Sun. This vast distance makes the planet extremely challenging to detect, as it could be relatively dim and far away, yet its gravitational effects might be enough to influence the orbits of debris in the Kuiper belt. Interestingly, the search for Planet 9 has become a topic of serious research and debate. Astronomers utilize advanced telescopes and computer simulations to explore potential locations for this elusive planet. As data accumulates, researchers hope to pinpoint its location and eventually capture a direct image of Planet 9, which could illuminate our understanding of the solar system's formation and evolution. Unraveling the mystery of Planet 9 could also spark discussions about the possibility of additional undiscovered planets lurking in the far reaches of our solar system. The dynamics of distant celestial objects hint at a rich and complex framework that still has many secrets waiting to be discovered. As more observations are made, the quest to find this enigmatic planet continues to inspire both scientists and astronomy enthusiasts alike. Saturn's hexagonal storm at its north pole is one of the most intriguing and unique weather phenomena observed in our solar system. This striking six-sided pattern, about 14,000 miles wide, has fascinated scientists since it was first discovered by the Voyager spacecraft in the 1980s. The enduring shape of this massive storm raises questions about the complex dynamics of Saturn's atmosphere. The hexagon is believed to be a result of a complex interplay of atmospheric flows rather than a singular storm. It forms from the interaction of fast-moving winds in Saturn's atmosphere, which create a standing wave pattern. The cold winds of Saturn's polar region travel at speeds exceeding 150 miles per hour. These winds generate a rotational effect combined with the planet's rapid rotation, resulting in the distinct geometric shape of the hexagon. Researchers have utilized fluid dynamics experiments to replicate this hexagonal structure in laboratory conditions. When they create a rotating fluid system and introduce an obstacle in the flow, a hexagonal pattern emerges. This suggests that the hexagon on Saturn is stabilized by the underlying fluid dynamics of the planet's atmosphere. Seasonal changes also play a role, as variations in sunlight and temperature affect wind patterns and can alter the appearance or intensity of the hexagonal storm. The hexagon is not just a static feature, it exhibits changes and dynamics of its own, showing smaller storms forming and moving along its edges. Remarkably, it has persisted for decades, if not longer, indicating a robust atmospheric system that continues to intrigue scientists. Understanding the hexagonal storm not only reveals the complexity of Saturn's weather, but also deepens our knowledge of fluid dynamics on a planetary scale. Uranus is unique among the planets in our solar system due to its dramatic tilt, which causes it to rotate on its side. While most planets have axial tilts of less than 30 degrees relative to their orbits around the Sun, Uranus boasts a tilt of about 98 degrees. This peculiar orientation sets it apart and gives rise to a distinct set of seasonal patterns and atmospheric behavior. The leading theory for Uranus's unusual tilt involves a massive collision with one or more celestial bodies during its formative years. Such a significant impact could have knocked the planet off its original axis, resulting in the extreme tilt observed today. This theory aligns with the notion that large collisions were common in the early solar system, which could have easily altered the rotational axes of planets. In addition to its axial tilt, Uranus's rotation is also noteworthy because it spins very slowly on its axis, taking about 17 hours to complete one rotation. As a result, each pole experiences long periods of sunlight followed by extended darkness, leading to extreme seasonal variations. The orientation of Uranus in relation to its orbit allows one hemisphere to be continuously exposed to sunlight for an extended period, while the other hemisphere remains in darkness. Furthermore, the unusual tilt of Uranus influences its atmospheric dynamics. The planet's weather is characterized by high-speed winds and shifting cloud patterns, providing an intriguing glimpse into the complex processes at work. As researchers continue to study Uranus, the mysteries surrounding its tilt and rotation offer valuable insights into planetary formation and the turbulent history of our solar system. The origins of Mars' moons, Phobos and Deimos, have intrigued scientists for years, sparking various theories about how these small celestial bodies came to orbit the red planet. Phobos, the larger of the two moons, and Deimos are both irregularly shaped and relatively small compared to Earth's moon, measuring about 14 and 8 miles in diameter, respectively. Their unusual characteristics lead astronomers to believe that they may not be native to Mars, but rather captured asteroids from the asteroid belt. The most widely supported hypothesis suggests that Phobos and Deimos are remnants of a larger population of rocky bodies in the asteroid belt. The notion is that early in our solar system's history, gravitational interactions could have pulled these objects towards Mars, enabling them to become satellites of the planet. The close resemblance in composition between Phobos and some types of asteroids, particularly the carbonaceous chondrites, further supports this theory of capture. Another compelling aspect of the case for their origin is the low density of both moons, indicating a composition rich in carbonaceous materials and possibly ice. This aligns with characteristics of certain asteroids, hinting that Phobos and Deimos formed elsewhere in the solar system before being caught in Mars' gravitational pull. Their irregular shapes and the significant cratering they exhibit also suggest a history of impacts, comparable to that of many other small bodies in the solar system. However, alternative theories also exist, including the possibility that they were formed in situ, resulting from debris ejected into Mars's orbit from impacts on the planet itself. Despite the various hypotheses, the nature of Phobos and Deimos remains a topic of ongoing research. Future missions targeting these moons may yield new insights, helping to shed light on the intriguing history of Mars and its unique companions. Beneath Europa's thick, icy crust is one of the most compelling candidates for potential extraterrestrial life in our solar system. It is believed that this moon of Jupiter possesses a subsurface ocean, hidden beneath an impressive layer of ice that may be several miles thick. Scientists estimate that this ocean could contain more than double the amount of water found on Earth, making Europa a particularly fascinating subject of study. The presence of liquid water is a critical factor when searching for extraterrestrial life. Water is often considered the universal solvent essential for biochemical processes. The ocean beneath Europa's icy exterior is thought to be in contact with the moon's rocky mantle, allowing for chemical exchanges that could create a suitable environment for life. Just as hydrothermal vents on Earth harbor diverse ecosystems, scientists speculate that similar processes could occur at the seafloor of Europa, where mineral-rich water could nourish potential microbial life forms. Data from missions like Galileo and observations from the Hubble Space Telescope have shown evidence of plumes of water vapor erupting from Europa's surface. These plumes provide tantalizing clues about the composition of the subsurface ocean, hinting at the possibility of organic molecules. Analyzing these features may reveal more about the moon's potential habitability without the need to drill through the ice. Future missions, such as NASA's Europa Clipper, aim to investigate the moon's icy crust and assess its potential for life more thoroughly. These explorations could unlock the secrets of Europa's hidden ocean and examine the conditions that might allow life to thrive in environments far different from those on Earth. The idea of discovering life beneath the ice of Europa captivates scientists and humanity alike, posing profound questions about our place in the universe. Mercury's composition is strikingly different from that of the other terrestrial planets. Notably, it possesses an unusually large iron core, which accounts for about 70% of the planet's total mass. This disproportionate presence of iron has puzzled scientists and has led researchers to delve into Mercury's formation and the processes that shaped it in the early solar system. One prevailing theory suggests that Mercury's large iron core is a result of a massive impact during its formation. As the planets in our solar system were forming, numerous collisions among protoplanetary materials were common. A significant collision could have stripped away much of Mercury's outer silicate mantle, leaving behind a larger proportion of the dense iron core. The remaining mantle is relatively thin compared to those of other planets, which emphasizes the dominance of the core in Mercury's overall structure. Another contributing factor could be the planet's proximity to the Sun. Being the closest planet, Mercury experienced higher temperatures during its formation, which may have influenced the differentiation of materials. The heat could have caused lighter compounds to evaporate or be pushed outward, while denser ions sank to form the core. This differentiation process might have been more extreme for Mercury than for other terrestrial planets like Earth, Venus, and Mars. Furthermore, Mercury's evolution is also influenced by its geological history. The planet has shown evidence of volcanic activity, and it is believed that this may have occurred after its core was established. Understanding the current structure of Mercury, including its core and mantle, gives us valuable insights into planetary formation and the unique conditions that can lead to such distinct characteristics in celestial bodies. As we learn more about Mercury through ongoing and future missions, the enigmatic nature of its large iron core becomes clearer, deepening our understanding of the history of our solar system. The mysterious spokes observed in Saturn's rings are fascinating features that have puzzled scientists since they were first discovered in the 1980s by the Voyager spacecraft. These spokes appear as radial structures that can extend for thousands of kilometers and seem to change in intensity and form over time. Their transient nature, combined with their striking appearance, makes them one of the most intriguing phenomena associated with Saturn's iconic rings. The prevailing theory for the formation of these spokes suggests that they are caused by the interaction of charged dust particles within the rings and Saturn's magnetic field. The spokes are thought to be composed of fine particles that become electrically charged by sunlight and interactions with the planet's magnetic field. This charging process allows the particles to become suspended in the rings, giving rise to the visible features as they interact with varying magnetic forces and gravitational influences. Observations have indicated that these spokes typically appear more prominently when Saturn is close to its equinox, a time when the Sun casts shadows more directly in the rings. This seasonal effect influences the brightness and visibility of the spokes, suggesting that they may be affected by changes in lighting conditions. When Saturn's rings are illuminated in a certain way, the charged particles may align or cluster together, creating the striking linear patterns we observe. Despite ongoing research, many aspects of the spokes remain elusive, resulting in differing hypotheses about their formation and behavior. Some scientists postulate that the spokes could be related to the dynamics of the ring particles themselves, or even influenced by the gravitational interaction of nearby moons. As new missions and improved observational techniques continue to provide data on Saturn and its rings, we may gain a better understanding of these captivating and enigmatic structures in one of the most breathtaking systems in our solar system. The formation of Pluto and its largest moon, Charon, presents a fascinating story that has intrigued scientists for decades. Both celestial bodies reside in the Kuiper Belt, a region beyond Neptune populated by many small icy objects. The prevailing theory suggests that Pluto and Charon formed from the same primordial material that comprised other bodies in the Kuiper Belt during the early days of our solar system. According to this model, Pluto and Charon likely formed through a process called accretion. In this scenario, dust and ice particles coalesced in the cold outer reaches of the solar system to gradually build up larger bodies. As these particles collided and stuck together, they formed larger planetesimals. Over time, under the influence of gravity, these objects continued to collide and merge, resulting in the formation of Pluto. This process would also allow for smaller bodies to coalesce into Charon, which is unusually large in comparison to Pluto, making it unique among large moons in our solar system. However, the relationship between Pluto and Charon is particularly intriguing. The size ratio between the two, where Charon is roughly half the diameter of Pluto, suggests that their formation involved a significant impact event. Some scientists theorize that Charon may have formed after a massive collision knocked a significant amount of material from Pluto. This debris would then have coalesced to form Charon, resulting in the highly synchronous relationship we observe today, where both bodies are tidally locked to each other, always showing the same face. Further studies of the Pluto-Charon system, including data from NASA's New Horizons mission in 2015, have provided valuable insights into their composition and geology, revealing a complex history. Understanding their formation not only sheds light on the dynamics of the Kuiper Belt, but also provides broader implications for the processes that shape the solar system as a whole. With ongoing research, we continue to learn about these distant worlds and the cosmic events that brought them into existence. The bright spots on the dwarf planet Ceres are among the most intriguing features observed in our solar system. Ceres, located in the asteroid belt between Mars and Jupiter, has captured the attention of scientists since NASA's Dawn spacecraft began its mission to study the dwarf planet in 2015. The most striking of these bright spots are found in a region called Okator Crater and have sparked considerable interest regarding their composition and origin. These bright spots are believed to be composed primarily of sodium carbonate, a type of salt, along with other reflective materials. The brightness is likely due to the way sunlight interacts with the surface, highlighting how differently the bright spots reflect light compared to the surrounding terrain. Spectroscopic analysis has indicated the presence of certain salts, suggesting that these materials may have originated from briny water beneath Ceres' surface. When the liquid water, rich in these salts, rose and evaporated, it left behind the bright residues we observe. The presence of these bright spots indicates that Ceres may have experienced cryovolcanism, or cold volcanism, in the past. This geological process involves the eruption of icy materials, as opposed to molten rock. The idea is that warm, salty water may have pushed through cracks in Ceres' crust, leading to the formation of the bright deposits. The ongoing study of these areas has revealed several features such as domes and mounds that may further suggest past geological activity. Understanding the bright spots on Ceres is significant for multiple reasons. They not only provide insights into the dwarf planet's geological history, but also have implications for the broader study of icy bodies in our solar system. The presence of water, even in frozen or briny form, raises questions about the potential for past habitability or the existence of life in such extreme environments. As research continues, the bright spots of Ceres remain a focal point of investigation, revealing the complexity and richness of this intriguing celestial body. Inside a black hole's event horizon lies one of the most mysterious and extreme environments in the universe. The event horizon represents the boundary beyond which nothing can escape the formidable gravitational pull of the black hole, including light. Beyond this threshold, the concept of location and time becomes profoundly altered due to the intense gravitational forces at play. As anything crosses the event horizon, it is believed to be drawn inexorably towards the singularity, the core of the black hole where density becomes infinite and the known laws of physics break down. At this point, space and time lose their familiar meanings. Current theories suggest that all paths, regardless of direction, ultimately lead to the singularity, creating a one-way journey for anything that ventures too close. This irreversibility is what defines the event horizon as a point of no return. The environment within the event horizon is also characterized by extreme tidal forces. Near the singularity, gravitational pull differs dramatically between the parts of an object closest to the center of the black hole and those farther away. This disparity can result in a process known as spaghettification, where objects are stretched vertically and compressed horizontally, resembling strands of spaghetti. This effect occurs due to the warping of space-time caused by the black hole's immense gravity. Given the current state of physics and our understanding of black holes, much about what occurs within the event horizon remains speculative. As scientists continue to explore the interplay of general relativity and quantum mechanics, questions about the nature of space-time, information conservation, and the fate of matter and energy subjected to these extreme conditions will persist. The quest to understand black holes and what lies within them is not only a journey into the depths of these enigmatic objects, but also a profound exploration of the fabric of the universe itself. The formation of supermassive black holes at the centers of galaxies is an intricate process that remains an active area of research in astrophysics. These giants can reach masses equivalent to millions or even billions of times that of our Sun, and their presence influences the dynamics and evolution of their host galaxies. Understanding how they form involves several interconnected theories. One of the leading hypotheses suggests that supermassive black holes emerge from the merging of smaller black holes and dense stellar clusters. In the early universe, the rapid collapse of massive clouds of gas and dust could lead to the creation of numerous smaller black holes. As these black holes drift through the surrounding matter, while also accreting gas, some may eventually coalesce through gravitational interactions, forming larger black holes over time. Another important factor is the role of the environment in which galaxies evolve. In the dense centers of galaxies, interactions among stars and gas clouds can lead to more efficient accretion of material onto these black holes. As they accumulate more mass, they may emit enormous amounts of energy, often observed as quasars, which are incredibly bright and energetic centers of active galaxies. This intense light occurs when gas spirals into the black hole, leading to extremely high temperatures and radiation. The growth of supermassive black holes can also be linked to the overall evolution of galaxies. Mergers between galaxies, common throughout cosmic history, can funnel gas and stars into the central regions, enhancing the growth of existing black holes. Such interactions not only contribute to their mass, but also shape the structure and dynamics of the galaxies involved. The balance between black hole growth and the galactic environment plays a significant role in the evolution of both. Despite these theories, many details of supermassive black hole formation remain unresolved. Research continues to explore how these enormous entities manage to form so quickly after the Big Bang, and how they interact with their host galaxies over cosmic time. Ongoing observations using advanced telescopes are critical in uncovering more about the nature and formation processes of supermassive black holes, providing deeper insights into the interactions between black holes and the galaxies they inhabit. Fast radio bursts, known as FRBs, are highly energetic and extremely brief flashes of radio waves that have captured the attention of astronomers and astrophysicists around the world. First discovered in 2007, these enigmatic signals last only a few milliseconds, yet they release an astonishing amount of energy, equivalent to what the Sun emits over the course of 10,000 years. Understanding their origins and mechanisms has become a significant area of research in the field of astrophysics. The exact cause of fast radio bursts remains uncertain, leading to a variety of theories about their origins. One prominent hypothesis suggests that FRBs could be produced by extraordinary cosmic events, such as the collapse of a neutron star or the merger of neutron stars, where extreme gravitational and magnetic forces generate intense bursts of energy. Another possibility includes the interactions of magnetars, highly magnetic and rapidly rotating neutron stars, with their surrounding environments. These magnetar bursts can create powerful bursts of radiation, which could potentially manifest as FRBs. Furthermore, some of the more exotic theories propose that FRBs might be linked to processes in the early universe, such as the formation of black holes or even signals from advanced extraterrestrial civilizations. While the latter idea is tantalizing, the scientific community generally focuses on natural astrophysical phenomena as the sources of these radio bursts. Recent advancements in observational technology have allowed astronomers to pinpoint some FRBs to specific galaxies, providing clues about their origins. Notably, some FRBs are found to repeat, suggesting they are associated with localized energetic astrophysical sources. The ongoing study of fast radio bursts continues to yield exciting discoveries, bringing us closer to understanding these elusive cosmic phenomena. As scientists work to decode their mysteries, FRBs contribute to our broader knowledge of the universe and the many dynamic processes occurring beyond our planet. Magnetars are a fascinating class of neutron stars known for their incredibly powerful magnetic fields, which can reach strengths exceeding 1 trillion Gauss, making them the most magnetically powerful objects in the universe. The origin of these immense magnetic fields is rooted in the processes that occur during the formation of neutron stars, as well as in the unique properties of their dense and compact matter. When a massive star exhausts its nuclear fuel, it undergoes a supernova explosion, collapsing under its own gravity. The core can shrink into a neutron star, a remnant of the original stellar core, where neutrons are packed together tightly due to extreme gravitational forces. As this collapse occurs, several essential factors contribute to the formation of a magnetar's intense magnetic field. One leading theory suggests that during the rapid rotation of the collapsing star, the conservation of angular momentum causes the existing magnetic field to be amplified. The dense matter within a neutron star, combined with the intense rotation and the factors involved in the supernova explosion, can lead to a dynamo effect. As the star spins, it generates a magnetic field that can be magnified significantly in strength. Additionally, the conditions within a neutron star are extreme. At such high densities, matter behaves differently than in ordinary conditions, allowing for complex interactions that contribute to the generation of magnetic fields. The presence of superfluid neutrons and the phenomena associated with them can also influence the magnetic field structure. In a magnetar, these fields can emerge rapidly, resulting in a core that can sustain and maintain an extraordinarily strong magnetic field. Furthermore, the immense energy associated with magnetars can lead to the gradual decay or rearrangement of the magnetic field over time. As magnetars age, they can occasionally release bursts of energy or flares due to the magnetic field's reconfiguration, releasing vast amounts of energy and emitting radiation across multiple wavelengths. This unique behavior reveals not only the potency of magnetars, but also their complex evolution and interactions with their surrounding environment. Ongoing research into these stellar phenomena continues to enhance our understanding of the physics behind their powerful magnetic fields and the implications for their study in the universe. Dark energy is a mysterious force that permeates the universe and is responsible for its accelerated expansion. Discovered in the late 20th century through observations of distant supernovae, scientists found that the universe is not only expanding but doing so at an increasing rate. This revelation sparked intense interest and research into what dark energy truly is. Approximately 70% of the universe is thought to consist of dark energy. Despite its prevalence, its exact nature remains elusive. One leading explanation posits that dark energy is a property of space itself. As space expands, more dark energy appears, creating a feedback loop that propels further acceleration. This concept is rooted in Einstein's theory of general relativity, which allows for a cosmological constant, a term that can account for the energy density of empty space. Alternative theories suggest that dark energy might be a dynamic field that changes over time, affecting the acceleration in different eras of cosmic history. Some scientists speculate that it could be linked to modifications to gravity on a cosmic scale. Each of these theories attempts to reconcile observations with our understanding of fundamental physics, but none have yet provided a definitive explanation for the phenomenon. Exploring dark energy represents one of the major challenges in modern cosmology. Its discovery has led to more questions than answers, prompting scientists to develop new observational techniques and theoretical models. Unraveling the secrets of dark energy could not only help us understand the fate of the universe, but also deepen our comprehension of the fundamental laws that govern cosmic evolution. Quasars are among the most luminous objects in the universe, often outshining entire galaxies. Their immense energy output arises from the activity surrounding supermassive black holes located at the centers of distant galaxies. As matter spirals into these black holes, it forms an accretion disk, which consists of gas, dust, and other materials that become incredibly hot due to friction and gravitational forces. This process transforms potential energy into thermal energy, resulting in extraordinary levels of light and radiation. The temperatures in the accretion disk can soar to millions of degrees, causing the material to emit powerful electromagnetic radiation across the spectrum, including visible light, ultraviolet light, and X-rays. The energy output from quasars can reach levels that are 1,000 times greater than that of all the stars in a typical galaxy combined. This overwhelming brightness is why quasars are detectable across vast distances, allowing astronomers to observe them from billions of light-years away. Another contributor to the energy production in quasars is the relativistic jets emitted along the axis of rotation of the black hole. These jets are composed of charged particles that are accelerated to near the speed of light, releasing additional energy in the form of radiation. These jets can extend over vast distances, sometimes thousands of light-years, and they can also influence their host galaxies by imparting energy and momentum on surrounding matter. The study of quasars enhances our understanding of the evolution of galaxies and the universe itself. By examining their properties, including their brightness and spectrum, astronomers glean insights into the conditions of the early universe and the processes governing black hole formation and growth. Quasars serve as cosmic beacons, illuminating the depths of cosmic history and the complexity of the forces driving the universe's evolution. Gamma-ray bursts are the most powerful explosions observed in the universe, releasing immense amounts of energy in the form of gamma rays, which are the most energetic form of light. These extraordinary events are thought to occur during the deaths of massive stars or through the merging of compact objects, such as neutron stars or black holes. In the case of massive stars, when they exhaust their nuclear fuel, they can collapse under their own gravity, resulting in a catastrophic implosion followed by a supernova explosion. If the core collapse is accompanied by powerful jets of material, these jets can produce the gamma rays that characterize the burst. When a neutron star merges with another neutron star or a black hole, the result can also lead to a gamma ray burst. In this scenario, the merging process releases tremendous gravitational energy and can create a rapidly rotating black hole surrounded by an accretion disk. As material is drawn into the black hole, powerful jets are ejected along its rotational axis. If these jets are aligned with Earth, we observe them as a gamma-ray burst. Gamma-ray bursts are divided into two main categories: long-duration bursts, which last from a couple of seconds to several minutes, and short-duration bursts, usually lasting less than 2 seconds. Long-duration bursts are primarily associated with the death of massive stars, while short-duration bursts are commonly linked to the merging of compact objects. This distinction helps scientists understand the different environments and conditions that lead to these explosive phenomena. The energy released in a gamma-ray burst can be staggering, often exceeding the total output of our Sun over its entire lifetime in just a matter of seconds. These bursts are so bright that they can be seen across vast cosmic distances, enabling astronomers to study these phenomena and gain insight into the extreme processes that occur in the universe. Understanding gamma-ray bursts not only sheds light on stellar evolution and the behavior of black holes, but also challenges our comprehension of fundamental physics under extreme conditions. Binary star systems, which consist of two stars gravitationally bound to one another, often form from the same dense region of gas and dust in a molecular cloud. When portions of the cloud collapse under gravity, they can fragment into smaller clumps, each of which begins the process of star formation. If two of these clumps are close enough, they will ultimately form stars that orbit each other. These initial conditions play a crucial role in determining the properties and evolution of the binary system. Once a binary system is formed, its evolution can take various paths depending on the masses of the stars involved and their orbital characteristics. If the two stars are similar in mass, they may undergo similar evolutionary stages concurrently, leading to complex interactions. As they evolve, they may expand and become red giants. If the stars are close enough, their outer layers can start to transfer mass between them, leading to phenomena such as mass exchange or even the formation of additional structures like accretion disks around a companion star. In cases where one star becomes significantly more massive than the other, it may eventually evolve into a supernova, leaving behind a neutron star or black hole. The companion star will continue its evolution independently. The dynamics of the system can change significantly during these moments, especially if the remnants of the supernova interact gravitationally with the companion star. Often, this can lead to scenarios like the formation of a binary neutron star system or a black hole neutron star pair, both of which can emit gravitational waves when they spiral toward each other. The study of binary star systems is essential for understanding stellar evolution and the mechanics of the universe. By observing these systems, astronomers can gather data on stellar masses, luminosities, and ages, contributing to broader models of how stars form, evolve, and ultimately impact their galactic environments. This exploration not only enhances our knowledge of stellar life cycles, but also informs theories about the distribution of matter in the universe. Cosmic rays are high-energy particles originating from outer space, and those with ultra-high energies are particularly intriguing to scientists. These cosmic rays can have energies exceeding 1 quintillion electron volts, which is millions of times more energetic than particles produced in human-made accelerators like the Large Hadron Collider. The origins of these ultra-high-energy cosmic rays remain a subject of active research, with several potential sources being investigated. One leading hypothesis suggests that ultra-high-energy cosmic rays originate from supermassive black holes located at the centers of active galaxies. These regions contain enormous amounts of energy and can accelerate protons and heavier nuclei to extreme speeds thanks to processes such as shock waves and magnetic fields in the vicinity of the black hole. As charged particles travel through intergalactic space and interact with photons from the cosmic microwave background, they can reach energies far beyond what is currently achievable in laboratory settings. Another proposed source of these high-energy particles is gamma-ray bursts, which are the most energetic events in the universe. During these explosive episodes, energy is concentrated in a very limited area, capable of accelerating particles to ultra-high energies. Additionally, certain types of supernova remnants and neutron star mergers are also considered potential sources, as they can create the necessary conditions for particle acceleration. Despite the proposed sources, determining the exact origins of ultra-high-energy cosmic rays is challenging due to their trajectory, which is influenced by magnetic fields present in interstellar and intergalactic space. As a result, tracking them back to their source can be nearly impossible. Advanced observational techniques using extensive air shower arrays and neutrino detectors aim to establish a clearer understanding of these cosmic rays, which could ultimately unravel the mysteries of extreme astrophysical processes in the universe. The answers to these questions may help deepen our comprehension of fundamental physics and the nature of the cosmos on the grandest scales. Type Ia supernovae are a spectacular and predictable type of explosion, often used by astronomers as cosmic yardsticks to measure distances in the universe. The origin of these events can be traced back to white dwarfs, which are the remnants of stars that have exhausted their nuclear fuel. A white dwarf consists primarily of carbon and oxygen and is supported against gravitational collapse by electron degeneracy pressure. For a white dwarf to ignite a type Ia supernova, it must undergo a process called accretion, where it gains mass from a companion star in a binary system. This companion can either be another ordinary star or another white dwarf. As the white dwarf accumulates material, particularly hydrogen and helium, its mass gradually increases. According to a well-established threshold known as the Chandrasekhar limit, when the white dwarf's mass approaches approximately 1.4 times the mass of the Sun, the temperature and pressure at its core become sufficiently high to initiate nuclear fusion. Once fusion ignites, it starts a rapid, uncontrollable process that converts carbon and oxygen into heavier elements. This reaction releases a tremendous amount of energy, causing the white dwarf to explode in a violent outburst. The explosion is not a typical stellar detonation. Instead, it occurs as a thermonuclear runaway. This means that the fusion reactions occur at an accelerated pace in a chain reaction manner, resulting in a cataclysmic release of energy that obliterates the white dwarf entirely and produces a vast amount of radioactive material. The aftermath of a type Ia supernova leads to the dispersion of heavy elements into space, enriching the surrounding interstellar medium. These elements contribute to the formation of new stars, planets, and ultimately life itself. The predictable luminosity of type Ia supernovae, stemming from the consistent mass of the exploding white dwarfs, allows astronomers to utilize them for measuring cosmic distances and studying the expansion of the universe. Understanding this process deepens our insight into stellar evolution and the life cycle of matter in the cosmos. The Milky Way galaxy, our home in the cosmos, is a barred spiral galaxy. This classification indicates that it has a central bar-shaped structure composed of stars, with spiral arms radiating outward from this core. However, the true shape of the Milky Way is complex and not perfectly defined. Scientists think of it as a flattened disk with a bulging center known as the galactic bulge and a halo of stars, gas, and dark matter surrounding it. The disk of the Milky Way is where most of its stars, including our Sun, are found. This region has a thickness of about 1,000 to 2,000 light-years, while its diameter spans approximately 100,000 light-years. Spiral arms, which are regions of higher density containing a large number of stars and star-forming regions, give the galaxy its distinctive appearance. These arms are thought to be formed by density waves that cause gas and stars to cluster together. Beyond the disk lies the galactic halo, a roughly spherical region filled with older stars, globular clusters, and dark matter. The extent of the halo is still uncertain, but it may stretch far beyond the visible parts of the galaxy, influencing its dynamics and the motion of its stars. This amorphous structure contributes to a more rounded shape when viewed from afar. Finally, observations using advanced technology, such as infrared and radio waves, have helped astronomers map the distribution of stars and gas in the Milky Way. While our perspective from within the galaxy limits definitive observations, ongoing research continues to refine our understanding of its true shape. These findings not only enhance our knowledge of our galaxy, but also provide valuable context in the broader study of galaxy formation and evolution in the universe. The Andromeda galaxy, known as M31, exhibits a fascinating characteristic: a double nucleus. This dual structure arises from the complex interactions and dynamics within the galaxy. The primary nucleus of Andromeda is a bright, centralized region containing a supermassive black hole, while the secondary component is thought to be the remnants of a smaller galaxy that was absorbed over time. As galaxies evolve, they can interact gravitationally with their neighbors, leading to phenomena such as mergers and tidal captures. Andromeda is currently in the process of merging with its satellite galaxies, which include M32 and NGC 2056. These smaller galaxies can leave behind stellar debris and remnants, contributing to the formation of a secondary nucleus. This secondary structure manifests as a less luminous yet distinctly separate concentration of stars and material. Additionally, the dynamics of the double nucleus are influenced by the galaxy's rotation and the distribution of dark matter in its halo. The gravitational interactions from Andromeda's mass, combined with the remaining star clusters from absorbed galaxies, create complex orbital patterns that maintain the double nucleus feature. Analysis of the velocities and movement of stars in these regions reveals the ongoing processes shaping the galaxy. Studying Andromeda's double nucleus not only deepens our understanding of this particular galaxy, but also provides insights into galaxy formation and evolution as a whole. The presence of multiple nuclei typically indicates a rich history of interactions and mergers, and Andromeda's evolution remains a subject of interest for astronomers looking to unravel the complex universe of galactic dynamics. The Fermi bubbles are two enormous symmetrical structures extending above and below the center of the Milky Way galaxy. One leading explanation posits that the Fermi bubbles are the result of outflows from the supermassive black hole at the center of the Milky Way, known as Sagittarius A star. When material falls into the black hole, it can be radiated as powerful jets of particles and energy. These jets may impact surrounding gas and dust, creating shock waves that push material outward, resulting in the formation of the bubbles. This energetic activity could be part of a past phase when the black hole was more active than it is today, possibly consuming more mass and expelling energy at a significantly higher rate. Another hypothesis suggests that the bubbles could be the remnants of cosmic rays accelerated and released during periods of intense star formation or supernova explosions in the central region of the galaxy. Massive stars end their lives in supernova events, which can inject vast amounts of energy and cosmic rays into the interstellar medium. Over time, the collective impact of these explosive events could accumulate, producing the large-scale structures observed as the Fermi bubbles. The Fermi bubbles provide crucial insights into the dynamics of our galaxy's core and the processes surrounding supermassive black holes. Ongoing research seeks to understand their exact formation mechanisms and the energy sources driving their existence. These investigations not only enhance our comprehension of the Milky Way, but also contribute to the broader understanding of how galaxies evolve and interact with the energetic phenomena associated with their supermassive black holes and stellar populations. The formation of spiral arms in galaxies, including our Milky Way, is a captivating process driven by gravitational interactions and dynamic structures within the galactic disk. These spiral arms are not fixed structures, but are dynamic features that emerge from the complex interplay of stars, gas, and gravitational forces. One of the key mechanisms responsible for the formation of spiral arms is the density wave theory. According to this theory, the spiral arms are created by the presence of density waves that travel through the disk of the galaxy. These waves cause stars and gas to clump together in certain regions, leading to increased density. As stars orbit the center of the galaxy, they move in and out of these density waves, which results in the characteristic spiral pattern. The waves act like traffic jams in a highway, causing vehicles, in this case stars and gas, to slow down and cluster together, thus enhancing the brightness and density of those regions. Additionally, star formation plays a critical role in shaping the arms. The regions of increased density often coincide with areas where new stars are actively forming, particularly in molecular clouds. The formation of young hot stars creates significant radiation and stellar winds, which can influence the surrounding gas and dust and further amplify the spiral structure. As these new stars eventually age and die, they contribute to the ongoing evolution of the spiral arms. Interactions between galaxies can also influence spiral arm formation. For instance, gravitational interactions from neighboring galaxies can create tidal forces that alter the dynamics within a spiral galaxy, possibly enhancing or reshaping its spiral arms. The complexity of these interactions means that spiral arms are continuously evolving features, intricately tied to the life cycles of stars and the gravitational influences of the galaxy and its companions. Understanding this process not only sheds light on the structure of spiral galaxies, but also provides valuable insights into the broader mechanics of galaxy formation and evolution in the universe. The Great Attractor is a massive gravitational anomaly located in the direction of the constellation Centaurus, approximately 100 million light-years away from Earth. It exerts a gravitational influence on galaxies within our local supercluster, the Laniakea supercluster, causing them to move towards it at significant velocities. The nature of the Great Attractor is complex and has been a subject of extensive research and investigation in the field of cosmology. At the core of the Great Attractor is a dense concentration of mass, primarily composed of galaxies, gas, and dark matter. This mass is estimated to be several 100,000 times that of our Milky Way galaxy. The gravitational pull from such a substantial concentration of matter is what drives the observed motion of galaxies in the region. Many galaxies, including our own, are being drawn towards this gravitational center as they respond to the combined gravitational effects of the mass surrounding the Great Attractor. One of the challenges in studying the Great Attractor is its location behind the plane of the Milky Way, which obscures many of the galaxies and structures that might provide a clearer picture of what lies at its center. Despite this, researchers have employed various observational techniques, including X-ray surveys and redshift measurements, to map the distribution of galaxies and the associated mass. Ultimately, the Great Attractor is part of a larger cosmic web structure that connects galaxy clusters and superclusters across the universe. Its existence indicates that the universe is not uniformly distributed, but rather organized into complex structures influenced heavily by gravitational forces. Ongoing research into the Great Attractor may reveal more about its role in shaping the cosmic landscape and provide further insights into the nature of dark matter and the dynamics of galactic movements on a grand scale. The presence of dark matter is a critical component in understanding the structure and dynamics of galaxies. However, some galaxies exhibit remarkably low amounts of dark matter, challenging previous assumptions about its pervasive role in the universe. These galaxies are often referred to as dark matter deficient or dark matter-free systems, and their existence provides valuable insights into the nature of dark matter and galaxy formation. One class of such galaxies is the so-called dwarf galaxies, which are smaller and less luminous than their larger counterparts. Some of these dwarf galaxies appear to contain a significant proportion of their mass in stars and gas, rather than dark matter. Researchers propose that interactions with larger galaxies or gravitational tides during their formation could have stripped these dwarf galaxies of their dark matter content. For example, if a dwarf galaxy merges with a more massive one, the gravitational effects can alter the distribution of dark matter and drive it away. Another explanation involves the formation conditions of these galaxies. Cosmological simulations suggest that smaller galaxies, particularly those that formed in less dense regions of the universe, may have had weaker gravitational well conditions during their formative years. As a result, they might not have been able to capture and retain the dark matter that typically surrounds larger galaxies. Additionally, the role of baryonic matter, which includes stars, gas, and dust, cannot be understated. In some cases, the observable matter may exert enough gravitational influence to dominate the dynamics of the galaxy, thereby obscuring the typical indications of dark matter. As a result, the movement of stars in these unique galaxies may suggest less dark matter presence than what is standard in most spiral and elliptical galaxies. The study of dark matter-deficient galaxies continues to deepen our understanding of the universe's structure and the role of dark matter in galaxy formation and evolution. By investigating these anomalies, scientists gain insights into the complex interplay between baryonic and dark matter, refining models of how galaxies develop and interact throughout cosmic history. The Boötes void is a vast, nearly empty region of space, encompassing about 100 million light-years across, and it is often described as one of the largest known voids in the universe. Within this extraordinary volume, there are far fewer galaxies than would typically be expected based on the average density in the universe. The unusual behavior of galaxies bordering the Boötes void prompts interest, as it appears that their dynamics and distributions are influenced by the void's unique environment. One reason for the peculiar behavior of galaxies in this region involves the effects of gravitational forces and cosmic expansion. The Boötes void's lack of mass concentration means that the gravitational pull from surrounding structures is weaker than in denser regions of space. As a result, galaxies that are near the edges of the void may experience different motion patterns compared to those in denser clusters. These galaxies may be less influenced by interactions with other galaxies, leading to more independent trajectories and potentially slower merger rates. Additionally, the Boötes void's emptiness might be related to the process known as gravitational repulsion. As galaxies move outward in an expanding universe, regions with lower densities, like the Boötes void, could experience less gravitational pull from the surrounding matter. This dynamic could lead to an anisotropic distribution of galaxies, where those on the fringes of the void exhibit less clustering and more uniform spacing, compared to the common grouping seen elsewhere. Another intriguing aspect of the Boötes void is that it contains a number of small, low-mass galaxies, along with a lack of larger, more luminous galaxy clusters. This absence of high-density environments can hinder efficient star formation and galaxy merging, shaping the evolution of these galaxies in specific ways. Over time, this dynamic may give rise to a distinct population of galaxies that evolve separately from their counterparts in more populated regions. Investigating the Boötes void not only enhances our understanding of cosmic structure, but also provides key insights into how galaxies behave in varying environments. Exploring the void's influence on galactic dynamics helps refine models of galaxy formation and evolution, revealing how local conditions can dramatically impact the life cycles of galaxies within the universe. Ultra-diffuse galaxies are a fascinating type of galaxy characterized by their low surface brightness and vast amounts of empty space between their stars. These galaxies are often difficult to detect because they contain only a small number of stars spread out over a large volume, resulting in a diffuse appearance. Their formation and survival involve unique processes that distinguish them from more conventional galaxies. One primary pathway to form ultra-diffuse galaxies is through interactions and mergers within denser regions of space, such as galaxy clusters. When galaxies collide and merge, the gravitational interactions can strip away their gas and stars. In some cases, this process can lead to the dispersal of stars into a larger, more diffuse configuration. Some studies suggest that these mergers create galaxies that lose their bright features, effectively transforming compact galaxies into ultra-diffuse ones as star formation slows or ceases altogether. Another important aspect of their survival relates to their low masses and dark matter content. Ultra-diffuse galaxies often have relatively small amounts of dark matter, which plays a critical role in their stability. Because they do not contain a significant gravitational force to hold galaxies together tightly, their structure may not collapse or fragment as quickly as in more conventional systems. This can allow them to persist for extended periods, even while interacting with other galaxies in clusters, where gravitational tides can exert influence. Interestingly, ultra-diffuse galaxies can also exist in low-density environments. In these settings, they may not engage in significant interactions with other galaxies, allowing them time to maintain their diffuse characteristics without being disrupted. The study of these galaxies sheds light on the broader range of galaxy types and evolution within different cosmic environments, revealing that galaxies can adopt a variety of forms based on their formation histories and the local gravitational landscape. Investigating ultra-diffuse galaxies opens up critical avenues for understanding galaxy formation and evolution, as they illuminate conditions under which galaxies can thrive despite their low density. This also raises questions about the processes that govern star formation in such systems, enriching the ongoing dialogue about the diversity of galaxies present in the universe. High-velocity clouds are intriguing structures found in the vicinity of the Milky Way galaxy. They are composed primarily of neutral hydrogen and exhibit unusual velocities that do not align with the expected motions of stars and gas in the galactic disk. These clouds present a unique opportunity to explore the complex interactions and processes at play within the galaxy and its environment. One prominent theory regarding the origin of high-velocity clouds suggests that they are remnants of material that has been ejected from the Milky Way due to various dynamic processes. For instance, supernova explosions, which occur at the end of a massive star's life cycle, can expel gas and dust into the surrounding space. The energy from these explosions can propel material outward at high speeds, leading to the creation of clouds that can be observed far away from their original locations. Another possibility is that these clouds are primordial structures, remnants from the early universe that have been somehow captured by the gravitational influence of the Milky Way. After the formation of the galaxy, some of the gas that contributed to star formation may not have been completely integrated into the stellar population or into the galactic disk. Instead, these primordial clouds could persist in the halo of the Milky Way, exhibiting high velocities as they orbit the galactic center. Moreover, high-velocity clouds cannot be completely decoupled from interactions with other galaxies. The Milky Way is part of a larger cosmic web in which galaxies interact gravitationally. Collisions, mergers, and tidal interactions with smaller galaxies or intergalactic gas can also contribute to the formation and movement of such high-velocity structures. Studies of high-velocity clouds continue to enhance our understanding of the Milky Way's dynamics and the processes governing galaxy evolution. By examining these clouds, astronomers can gain insights into the history of gas and star formation in the galaxy, as well as the interactions between the Milky Way and its surrounding environment. These explorations play a crucial role in piecing together the broader narrative of how galaxies form, evolve, and interact over cosmic time. Ring-like structures in galaxies are often the result of gravitational interactions. When two galaxies collide or pass by each other, their massive gravitational fields can distort the shapes of the galaxies involved. This interaction can strip away stars and gas, twisting the remaining matter into a ring shape. The classic example of this phenomenon can be seen in the Cartwheel galaxy, which showcases a beautiful, prominent ring-like structure formed due from a collision with a smaller galaxy. Another fascinating reason for these ring structures is the density wave theory. This theory explains that as a galaxy rotates, areas of higher density can develop, where more stars and gas are concentrated. These denser regions can form rings as they orbit the galaxy's center, creating a sort of resonant pattern in the spiral arms. This can lead to the formation of a ring of stars that can appear vividly when observed. Additionally, some ring-like structures can arise from the evolution of a galaxy's features over time. As galaxies age, they can experience internal processes such as stellar formation and the movement of gas. These processes can create distinctive patterns, leading to the appearance of rings composed of young, hot stars formed from gas that has been accumulated. These ring formations not only enhance the diversity of galactic shapes we observe, but also provide astronomers with crucial clues about the life cycle of galaxies. Studying these structures allows scientists to understand how galaxies interact with one another and evolve over billions of years. Each ring is a snapshot of galactic history, revealing the dynamic nature of our universe. The dimming of Betelgeuse, a red supergiant star in the constellation Orion, has captured the attention of both astronomers and stargazers alike. This phenomenon can be attributed to several factors. One primary reason is the star's natural variability. Betelgeuse is known to be a semi-regular variable star, exhibiting changes in brightness over periods of several months to years. This variability can result from pulsations in the star's outer layers, causing it to expand and contract, which subsequently alters its brightness. Another significant cause of Betelgeuse's dimming in recent observations has been attributed to dust formation. As the star undergoes changes, it can produce and eject large amounts of gas. When this gas cools, it can condense into dust particles, which could partially block the light emitted from the star, making it appear dimmer from our vantage point on Earth. This dust formation is a natural part of a star's life cycle and is indicative of the processes occurring in its outer layers. As for whether Betelgeuse is about to go supernova, the answer is more nuanced. While Betelgeuse is indeed nearing the end of its life, it could still be hundreds of thousands to a few million years before it explodes. The star has already exhausted much of its nuclear fuel and is in the late stages of stellar evolution. However, predicting the exact timing of a supernova is exceedingly complex. Scientists estimate that when Betelgeuse does ultimately explode, it will be a spectacular sight from Earth, potentially brighter than the Moon and visible during the day. Overall, Betelgeuse continues to intrigue astronomers, not only due to its current dimming, but also as a subject of study regarding the life cycle of massive stars. Understanding the processes affecting Betelgeuse provides valuable insight into the life cycle of similar stars and the eventual implications of their violent ends. Tabby's star, officially known as KIC 872-191, has become famous for its mysterious and unusual dimming patterns that have left astronomers puzzled and fascinated. Unlike typical variable stars, which dim in a regular and predictable manner, the dimming of Tabby's star occurs irregularly and can vary dramatically over short periods. This unpredictable behavior has sparked numerous theories about the underlying causes. One of the most well-discussed explanations is the possibility of a swarm of comets. The idea suggests that a large group of comets could be passing in front of the star, temporarily blocking its light and creating the observed dimming. As these comets travel through space and approach the star, their icy bodies can release dust, forming a cloud that partially obscures the light. This would result in the star appearing to dim and brighten in an erratic fashion. Another hypothesis involves the presence of a large structure orbiting the star, such as an alien megastructure. Although this idea has stirred much intrigue, it remains highly speculative. This theory posits that advanced civilizations might have constructed enormous structures to collect energy from the star, leading to the unusual dimming patterns. However, this remains a far-fetched scenario when compared to natural astrophysical explanations. Astrophysicists are also considering the potential effects of changes in the star's own atmospheric conditions or processes. For instance, non-uniform distribution of surface activity akin to sunspots could create variations in brightness. Additionally, the possibility of the star undergoing intrinsic changes in luminosity as it evolves may also contribute to the observed phenomena. As research continues, Tabby's star serves as a reminder of the complexities of stellar life and the vast unknowns that still exist within our universe. Thorne-Żytkow objects, named after the renowned physicists Kip Thorne and Anna Żytkow, represent an intriguing class of hypothetical stellar structures that challenge our understanding of stellar evolution. They are theorized to form when a red supergiant star undergoes a unique phase of evolution, allowing a neutron star to become embedded within its outer layers. This setup creates a fascinating dynamic between the two distinct stellar entities. The mechanics behind these objects hinge on the life cycle of massive stars. When a massive star exhausts its nuclear fuel, it typically expands into a red supergiant. If it explodes in a supernova and leaves behind a neutron star, circumstances may arise where the neutron star could be captured by the supergiant's gravitational field. In this scenario, the neutron star becomes immersed in the outer layers of the supergiant, while still exerting substantial gravitational influence, and interacting with the surrounding stellar material. One of the most captivating aspects of Thorne-Żytkow objects is the possibility of unusual nuclear processes occurring within them. The presence of the neutron star could lead to increased rates of nuclear reactions in the surrounding material, producing a variety of elements and possibly even altering the star's luminosity and temperature. This provides a theoretical basis for how such objects might appear different from regular stars in their surroundings. While no confirmed Thorne-Żytkow object has been found to date, astronomers continue to search for evidence of their existence. Detecting such objects would not only expand our understanding of stellar formation and deaths, but would also offer insight into the complex interplay between different types of celestial bodies. The concept of stars within stars challenges the traditional boundaries of what we consider stellar phenomena and highlights the richness of cosmic diversity in our universe. Blue straggler stars are a fascinating phenomenon found within globular clusters, and they stand out as younger, bluer stars in an environment typically dominated by older, cooler stars. Their youthful appearance has puzzled astronomers for decades, but several mechanisms have been proposed to explain how these stars maintain their seemingly vibrant characteristics amidst an aging population. One primary explanation involves stellar mergers. In the dense environment of a globular cluster, stars can come very close to one another, leading to interactions that may result in collisions. When two stars merge, they create a more massive star that can burn through its fuel more rapidly. This process not only produces a star that shines much brighter and hotter than its neighbors, but can also give rise to the blue color observed in blue straggler stars, as massive stars tend to emit light in the blue and ultraviolet spectrum. Another contributing factor to the presence of blue stragglers is the binary star system dynamics. In globular clusters, many stars are found in pairs or binary systems. In these configurations, mass transfer can occur from one star to its companion. If a more massive star in a binary system feasts on the hydrogen-rich material from its less massive partner, it can reignite nuclear fusion in the star that has gained additional mass, effectively rejuvenating it. This process allows the star to continue shining brightly and appear younger than its true age suggests. The interactions and dynamics within globular clusters play an essential role in the formation and existence of blue stragglers. These dense environments foster conditions conducive to stellar evolution that differs dramatically from what occurs in more isolated regions of space. Consequently, blue straggler stars not only provide insight into stellar evolution, but also highlight the complexities of stellar interactions in densely populated environments. As astronomers continue to study these intriguing stars, they uncover more about the processes that govern stellar life cycles and the evolutionary pathways that produce such extraordinary objects in the cosmos. Cepheid variable stars are renowned for their distinct and intense pulsations, which are crucial for measuring cosmic distances and understanding the scale of the universe. The pulsations in these stars are driven primarily by changes in their internal pressure and temperature associated with nuclear fusion processes. Cepheid variables undergo cycles of expansion and contraction, giving rise to their characteristic brightness variations. At the heart of a Cepheid star's pulsation is the balance between gravity, which pulls inward, and pressure from nuclear fusion in the star's core, which pushes outward. As the star's core heats up and generates energy through fusion, the outer layers expand. This expansion leads to a decrease in temperature and pressure in the star's outer regions. Eventually, the reduced pressure cannot support the outer layers against the force of gravity, causing the star to contract. As it contracts, the temperature rises again, reigniting the nuclear reactions, and the process repeats. The precise mechanics behind this pulsation are described by the theory of stellar dynamics, particularly the applications of the opacity mechanism. This concept refers to the way energy is transported through the star. Changes in temperature alter the opacity of the star's outer layers, which affects how energy escapes. When the layers expand, the opacity decreases, allowing energy to escape more easily. Conversely, during contraction, energy becomes trapped, leading to increased pressure that eventually causes the outer layers to expand once more. The time it takes for a Cepheid variable to go through one complete cycle of pulsation is directly related to its luminosity. The relationship between the pulsation period and the brightness of these stars was famously utilized by Henrietta Leavitt in the early 20th century, forming a cornerstone of modern astronomical distance measurement. Observations of this relationship help astronomers determine distances to faraway galaxies, eventually leading to insights about the expansion of the universe itself. The remarkable cycle of a Cepheid variable serves as both a cosmic clock and a vital tool in our exploration of the universe. Mira, a red giant star located in the constellation Cetus, is a fascinating example of a star that exhibits a comet-like tail, which is a result of its unique characteristics and behavior as it evolves. As Mira exhausts its nuclear fuel and transitions into a later stage of stellar evolution, it begins to lose mass at an increasing rate. This mass loss is primarily due to a powerful stellar wind, which is a stream of particles emitted from the outer layers of the star. As Mira sheds its outer layers, this ejected material can interact with the surrounding environment, forming a tail akin to that of a comet. The star's atmosphere is rich in gases and dust, and as it progresses in its life cycle, this material travels away from Mira, creating a long trail of ionized gas and dust particles. The tail's appearance is influenced by the velocity of the stellar wind and the density of the surrounding interstellar medium. An additional factor that contributes to the development of a comet-like tail is Mira's motion through space. As the star moves, it carries with it the material expelled by its stellar wind. When the stellar wind interacts with the interstellar medium, the stream of gas and dust can be shaped into a tail that extends in the opposite direction of the star's motion, similar to how a comet's tail forms as it approaches the sun and is affected by solar radiation and the solar wind. The presence of a tail in Mira not only signifies the mass loss experienced by aging stars, but also sheds light on the processes that govern stellar evolution. Observing stars like Mira helps astronomers understand the end stages of stellar life cycles and the transformation processes that lead to the formation of planetary nebulae, where the ejected material can contribute to the creation of new stars and planets in the cosmic cycle. These phenomena highlight the dynamic and interconnected nature of stellar life and the broader universe. Hypervelocity stars are a remarkable class of stars that travel through space at such incredible speeds that they can escape the gravitational pull of our Milky Way galaxy. These stars can reach velocities exceeding 1 million miles per hour, making them some of the fastest-moving objects in the universe. Their origins can be traced to several astrophysical phenomena, primarily involving interactions with supermassive black holes. One of the leading theories for the formation of hypervelocity stars revolves around encounters with supermassive black holes, such as the one located at the center of our galaxy. During certain gravitational interactions, a star can be pulled into the black hole's vicinity. In a two-star system, if one star is sent into a highly elliptical orbit around the black hole, the gravitational influence can dramatically alter the fate of both stars involved. If one star is gravitationally bound to the black hole while the other is flung outward, it can be propelled into a hypervelocity escape trajectory. Another scenario involves the interactions that occur during the merger of star systems. When binary stars come close enough, the gravitational forces at play can result in one star being ejected at high speed while the other falls into the black hole. This process not only sheds light on the dynamics of binary star systems, but also offers insight into the behaviors of stars in dense environments, such as globular clusters. Interestingly, research has revealed that hypervelocity stars can also be created through different mechanisms, such as dynamic interactions within star clusters, where close encounters between stars might assist in ejecting one or more stars into space at high velocity. These fast-moving stars may leave behind a trail of stellar debris and provide a glimpse into the dramatic interactions that occur in the crowded regions of the universe. The study of hypervelocity stars not only enhances our understanding of stellar dynamics and the behavior of stars influenced by gravitational forces, but also raises intriguing questions about our galaxy's structure and the future of these remarkable cosmic travelers. As they journey through intergalactic space, hypervelocity stars continue to shed light on the diverse and complex processes that shape the cosmos. Binary stars are pairs of stars that are gravitationally bound to each other, and they can engage in intriguing interactions, especially when it comes to exchanging mass. This mass transfer occurs primarily in systems where one star expands into a red giant or when the stars orbit closely, allowing the gravitational influence of one star to pull material from its companion. As one star in a binary system approaches the later stages of its evolution, it can swell and its outer layers can become less dense. If this star is in close proximity to its companion, gravitational forces can result in the more massive star losing material to its partner. This process is often facilitated by the formation of an accretion disk, where gas and dust from the outer layers of the swollen star spirals around the companion star before gradually being consumed. The characteristics of the stars involved dictate the efficiency of this transfer, with factors like temperature, distance, and mass all playing significant roles. The consequences of mass transfer in binary systems can be profound and varied. In many cases, mass transfer can rejuvenate the receiving star, providing it with additional hydrogen that can reignite nuclear fusion, effectively resetting its stellar clock. This rejuvenation is particularly evident in the case of blue straggler stars, which are born from such interactions, appearing hotter and younger than their neighbors. However, mass transfer can also destabilize a binary system, especially if one star becomes significantly more massive than the other. This imbalance can result in altered orbital dynamics and, in extreme cases, lead to one star being completely stripped of its outer layers. Additionally, if the mass transfer occurs rapidly, it may trigger explosive events such as novae or even a supernova if a white dwarf accumulates enough mass from its companion to reach a critical limit. The study of mass transfer in binary star systems provides essential insights into stellar evolution and the complex relationships between stars. Such interactions reveal how binary stars influence each other's life cycles and contribute to the dynamic processes shaping galaxies over time. B stars are a fascinating category of stars characterized by their high rotation rates and the presence of an equatorial disk of gas. The rapid rotation of these stars can be attributed to several factors, including their formation processes and the conservation of angular momentum during their evolution. Initially, B stars form from the collapse of a rotating molecular cloud. When this cloud collapses under gravity to form a star, the conservation of angular momentum plays a crucial role. As the material from the cloud gathers into a smaller region, it begins to spin faster, much like a figure skater pulls in their arms to spin more rapidly. This results in B stars having inherently high initial rotation rates as they develop. Throughout their life cycle, B stars maintain their high speeds due to their relatively low mass loss compared to other massive stars. While many stars expel significant amounts of material during their lifetimes, B stars do not lose mass as quickly. The presence of an equatorial disk, formed from the material shed from the star's outer layers, can also contribute to the specific dynamics of rotation. This disk of gas can influence the star's angular momentum and its overall rotation, allowing it to maintain high speeds. Additionally, interactions between B stars and their surrounding environments can affect their rotation rates. Close encounters with other stars or the dynamics of binary systems can exchange angular momentum, potentially speeding up a B star's rotation even further. This interplay between accretion of gas, differential rotation, and interactions with companion stars generates a complex environment that sustains the rapid rotation associated with B stars. The study of B stars provides valuable knowledge about stellar dynamics and evolution, as their rapid rotation, along with the effects of mass transfer and the presence of circumstellar disks, offers insights into the processes that shape massive stars in our galaxy and beyond. Massive stars, which are those with initial masses greater than about 8 times that of the Sun, generate immense energy through nuclear fusion in their cores. This process produces substantial radiation pressure, a force created by the energy emitted as light and other forms of radiation that acts outward, countering the inward pull of gravity trying to collapse the star. Yet, Despite this immense outward pressure, massive stars have evolved complex mechanisms that allow them to maintain stability throughout their lifetimes. One crucial factor is the balance between gravitational force and radiation pressure, known as hydrostatic equilibrium. In massive stars, the energy generated in the core through fusion reactions provides enough radiation pressure to counteract gravity effectively. Initially, hydrogen is fused into helium in the core, but as the supply of hydrogen dwindles, the star undergoes a series of fusions of heavier elements, such as helium into carbon and then oxygen, eventually producing even heavier elements. Each of these processes occurs at higher temperatures and pressures, enabling the star to sustain the necessary radiation pressure to avoid collapse. Moreover, as massive stars reach the later stages of their evolution, they often develop a layered structure. The core contains elements like iron, where fusion ceases to yield energy, and the outer layers consist of lighter elements undergoing fusion. The varying fusion processes occurring in different layers can help regulate the balance between radiation pressure and gravity, allowing the star to remain stable even as it evolves. Another fundamental mechanism involves the loss of mass through powerful stellar winds, which feeds back into the star's stability. As massive stars lose mass, they reduce their total gravitational pull, which helps mitigate the competition between gravity and radiation pressure. These winds also carry away energy, assisting in the moderation of radiation pressure within the star. Although mass loss is an inherent risk, it ultimately helps massive stars avoid catastrophic collapse until they reach the end of their life cycle. Ultimately, massive stars have developed these intricate mechanisms to manage the forces acting within them. This balance allows them to shine brightly for millions of years, culminating in spectacular endpoints such as supernova explosions, which mark the end of their remarkable life cycles. The processes at play within these giants reveal the complex relationships between gravity, temperature, and fusion, highlighting the dynamic nature of stellar evolution. Hot Jupiters are a fascinating class of exoplanets characterized by their large sizes and proximity to their parent stars, often orbiting at distances much closer than Mercury does to the Sun. The formation of these gas giants so near to their stars challenges traditional models of planet formation, leading astronomers to explore several possible explanations for their origins. Initially, it is believed that hot Jupiters form in the same way as other gas giants, primarily through a process known as core accretion. During the early stages of planet formation, protoplanetary disks of gas and dust surround young stars. In this environment, solid particles collide and stick together, forming larger masses or cores. Once a core reaches a sufficient size, it can attract surrounding gas and grow into a massive planet. However, the conventional expectation is that these gas giants should form in the cooler regions of the protoplanetary disk, far from their stars. To account for hot Jupiter's close orbits, researchers suggest that after their formation, these planets may undergo significant migration. This migration can happen through several mechanisms. One such mechanism is the interaction between the planet and the gas in the protoplanetary disk. As the planet moves through the disk, it can generate waves that transfer angular momentum, causing it to spiral inward towards its star. This process can happen relatively quickly, allowing the planet to settle into a close orbit. Another explanation involves gravitational interactions with other bodies in the protoplanetary disk. If a hot Jupiter forms alongside other planets, close encounters or mutual gravitational interactions can lead to a process known as planet-planet scattering. This can alter the orbits of the planets, allowing a hot Jupiter to be ejected into a closer orbit while the other planets move outward. Additionally, the presence of a binary star system can enhance migration. If a hot Jupiter resides in a system with two stars, the gravitational influence of the stars can shepherd the planet inwards, leading to its close proximity. The study of hot Jupiters has profound implications for our understanding of planetary formation and migration dynamics. Their existence raises intriguing questions about the behavior of planetary systems and the factors that govern their development. Investigating these close-orbiting gas giants continues to be a key focus in the search for understanding other planetary systems beyond our own. Some exoplanets exhibit retrograde orbits, which means they orbit their stars in the opposite direction to the star's rotation. This intriguing phenomenon can be attributed to several factors, including gravitational interactions and chaotic dynamics during the formation and evolution of planetary systems. One common explanation for retrograde orbits involves interactions with other massive bodies, particularly in systems with multiple planets. During the early stages of planetary formation, a disk of gas and dust surrounds a young star. In this environment, gravitational interactions can lead to scenarios where a newly formed planet may be influenced by the gravity of neighboring planets. If these interactions are strong enough, they can impart energy and alter the orbits of the planets involved, potentially flipping the orbit of a planet into retrograde motion. Another scenario involves close encounters with other star systems. If a binary star system or another star passes close enough to a planetary system, gravitational perturbations can drastically change the orbits of the planets. Such gravitational interactions may lead to a planet being ejected or pushed into a retrograde orbit around its host star. This process can be particularly relevant in dense stellar environments, such as globular clusters, where gravitational encounters are more likely to occur. In some cases, a planet can also form in a retrograde orbit due to the dynamics of the protoplanetary disk from which it originated. If the disk is asymmetrically distributed or experiences turbulence, it can lead to the formation of planets on orbits that differ in direction from the star's rotation. The study of retrograde exoplanets provides valuable insights regarding the dynamics of planetary systems and the complex interactions that govern their evolution. Understanding how these unusual orbits arise helps astronomers refine their models of planet formation and migration, revealing the rich diversity of scenarios that can emerge in the universe. Each retrograde exoplanet serves as a reminder of the complex and often chaotic nature of planetary dynamics in varying conditions. Super-Earths are a class of exoplanets characterized by their masses being larger than Earth's, but significantly smaller than those of Neptune or Uranus. Typically, these planets fall within the range of 1 to 10 times the mass of Earth. The formation of super-Earths is an intriguing topic that can offer insights into planetary formation processes and the dynamics of the early solar system. Like other terrestrial planets, super-Earths form through a process called core accretion. In the early stages of a protoplanetary disk, solid particles collide and coalesce to form planetesimals. Over time, these planetesimals collide and merge, forming larger bodies or planetary cores. For super-Earths, the formation likely occurs in a temperature and pressure regime where there is sufficient material to accumulate into larger rocky planets, potentially with substantial atmospheres. Once a solid core forms, it may begin to attract surrounding gas from the protoplanetary disk. The ability of a planet to attract gas is proportional to its mass, so super-Earths can accumulate significant gaseous envelopes, leading to their characteristic compositions. The variety in how much gas is captured may lead to differences between rocky super-Earths and those with thick atmospheres. As to why we do not observe any super-Earths in our solar system, the answer likely lies in the unique conditions and dynamics of our solar system's formation. The solar nebula, which was the cloud of gas and dust that formed the solar system, was relatively small compared to the environments where many super-Earths have been found. In our solar system, most of the material that formed the terrestrial planets was accumulated in the inner solar system, resulting in smaller rocky planets like Earth, Mars, Venus, and Mercury. Additionally, during the early phases of the solar system, gravitational interactions and migrations of giant planets, like Jupiter and Saturn, could have affected the formation of smaller planets. These giants may have cleared out the region where super-Earths could have formed by scattering material inward or outward, preventing the stable formation of larger terrestrial planets. The discovery of numerous super-Earths in other star systems suggests diverse formation processes and environments that differ from those of our own solar system. Studying these planets helps astronomers gain a deeper understanding of planetary formation and reveals the complexity of planetary systems across the cosmos. Each exoplanet provides a unique glimpse into the varied evolutionary pathways that can occur in the universe. The Neptunian desert refers to a peculiar gap in the distribution of exoplanets, characterized by a scarcity of planets with masses or radii similar to that of Neptune, which is about 4 times the size of Earth. This phenomenon has become a significant topic of discussion among astronomers as they study the diversity of planetary systems discovered outside our own. The desert manifests itself as a notable lack of exoplanets in the range of approximately 2 to 4 times the Earth's radius, creating a clear dearth of Neptunian-type planets. One explanation for the existence of this gap is related to the different formation and evolution processes that dictate how planets develop and migrate after their formation. When planets form in a protoplanetary disk, they can undergo several pathways based on their mass. If a planet is massive enough, it may retain a thick atmosphere and become a gas giant, similar to Jupiter or Saturn. If it is smaller, it can lose its gaseous envelope and evolve into a rocky planet. The Neptunian desert can be understood in the context of how these processes result in the observed distribution of exoplanets. Planets that form with intermediate masses, those around the size of Neptune, might either lose their atmospheres due to factors like intense stellar irradiation, or develop into gas giants by accumulating more gas from the protoplanetary disk before it dissipates. This transition results in a very small number of planets being left in the size range characteristic of Neptune, thereby creating the observed gap. Another significant factor is the role of stellar irradiation and atmospheric loss. For planets within the habitable zone of their stars, high levels of stellar radiation can cause lighter gases like hydrogen and helium to be stripped away over time. Consequently, super-Earths, which are often situated in the same regions as exoplanets that would have otherwise been classified as Neptunian, are more likely to exist. This process can reconfigure the population of planets, leading to fewer planets of Neptune-like characteristics. Understanding the nature of the Neptunian desert illuminates not only the processes involved in planetary formation, but also the implications of stellar and environmental conditions in shaping planetary systems. Ongoing surveys and discoveries of exoplanets continue to challenge and refine our models, enabling a more profound comprehension of the diverse array of worlds beyond our solar system. Exoplanets that orbit close to their stars face an intriguing challenge, namely, surviving the intense conditions found within a star's corona. The corona, which is the outer atmosphere of a star, can reach temperatures of millions of degrees, creating a hostile environment filled with radiation and particle streams. Despite this seemingly inhospitable climate, some exoplanets manage to thrive, often thanks to a combination of unique factors. One key to their survival lies in the strength of their magnetic fields. Planets with strong magnetic fields can protect their atmospheres from being stripped away by the stellar wind, which is a stream of charged particles ejected from the star. This shielding effect allows the planets to retain the essential components of their atmospheres, which is crucial for maintaining conditions that can support the possibility of life. Additionally, these magnetic fields can also act as a barrier against harmful radiation, further mitigating the impacts of the star's energetic environment. Another important aspect is the composition and thickness of the planet's atmosphere. Some exoplanets have developed substantial atmospheres that can absorb and deflect much of the incoming radiation and heat from their host star. These atmospheres may consist of gases that are particularly effective at insulating the planet's surface, allowing temperatures to remain within a range that could support liquid water and, by extension, the potential for life. Moreover, the orbital dynamics of these planets can play a significant role. Many of the planets that reside within a star's corona are tidally locked, meaning one side always faces the star while the other remains in perpetual darkness. This unique rotation could lead to temperature gradients that allow for the presence of oceans or ice, creating a diverse range of environments on the planet itself. Such intricate interactions between magnetic fields, atmospheric conditions, and orbital mechanics illustrate just how resilient these exoplanets can be in the face of extreme stellar phenomena. Extreme temperature variations on tidally locked exoplanets arise from their unique rotational dynamics. These planets rotate in such a way that they always show the same face to their star, creating a stark contrast between the day side, which is perpetually illuminated and heated, and the night side, which remains in darkness and experiences significantly lower temperatures. This phenomenon leads to a dramatically uneven distribution of heat. On the day side, temperatures can soar to scorching levels due to the constant exposure to stellar radiation. In some cases, this could even lead to the evaporation of surface water or the formation of clouds that trap heat, further amplifying the extreme conditions. The continuous influx of energy from the star creates an environment where high temperatures dominate, often giving rise to fierce winds that assist in redistributing heat across the planet. Conversely, the night side faces an entirely different scenario. Here, temperatures can plummet to frigid levels as the planet lacks direct sunlight for prolonged periods. Without the warming influence of the star, the atmosphere can cool dramatically, potentially leading to the formation of frost or ice, especially if the planet has a significant atmosphere capable of holding heat. This stark thermal contrast not only defines the planetary experience, but also influences atmospheric circulation patterns, which can drive powerful winds that seek to balance the temperature differences. Additionally, some tidally locked exoplanets may possess thick atmospheres that can help mitigate these temperature variations to some degree. A robust atmosphere has the potential to redistribute heat from the day side to the night side, although the efficiency of this process varies widely depending on the planet's characteristics and atmospheric composition. Such dynamics create a fascinating and complex interplay, revealing the remarkable ways in which these distant worlds respond to their stellar environments. Binary star systems, where two stars orbit around a shared center of mass, present a unique environment that significantly influences planetary formation and stability. Unlike single star systems, the gravitational dynamics in binary systems can create complex interactions that affect the formation processes of planets. The presence of a second star can alter the amount of material in the protoplanetary disk, the rotating disk of gas and dust from which planets form. In a binary system, the gravitational pull of both stars can help shape the protoplanetary disk's structure. Depending on the distance between the two stars, their gravity can either enhance or hinder the accumulation of materials necessary for planet formation. In wider binaries, the disk may remain relatively stable, allowing for the gradual clumping together of particles to form larger planetary bodies. However, in closer binaries, the gravitational perturbations can lead to a more chaotic environment where particles may be scattered or ejected from the disk entirely. Such dynamics significantly affect where planets can form and how many can exist in the system. The stability of planets orbiting a single star also becomes complicated in a binary system. For planets that manage to take shape, their orbits can be influenced by the gravitational pull of the second star. This can lead to unstable orbits that might periodically destabilize a planet's trajectory, increasing the risk of collision with other bodies or even ejection from the system. Consequently, planets residing in these systems often have to navigate a very different gravitational landscape compared to those orbiting single stars. Interestingly, some planets can find stable zones within a binary star setup. If situated at the right distance from each star, they can achieve gravitational balance, allowing them to maintain stable orbits without dramatic perturbations from either star. These so-called circumbinary planets can exist within a particular region in the protoplanetary disk that is influenced by both stars, showcasing the intricate balance of forces at play. The fascinating nature of binary star systems thus opens up pathways for diverse planetary environments, leading to possibilities that are as varied as the stars themselves. Exoplanets described as cotton candy worlds exhibit remarkably low densities, which suggest compositions that differ significantly from terrestrial planets like Earth. The term commonly refers to these planets' fluffy and gaseous characteristics, leading to suspicions of their making up lighter materials. These low-density worlds often have a gaseous envelope that is less massive than what one might expect, mixed with volatile elements. Most cotton candy exoplanets are thought to possess substantial atmospheres primarily composed of hydrogen and helium, similar to the gas giants of our solar system. However, what sets them apart is their comparatively low mass and rapid formation, which may result in a bloated, puffed-up state. As these planets develop, they can trap large amounts of lighter gases, creating a puffy, less dense exterior that resembles cotton candy in terms of softness and volume compared to its mass. Additionally, the presence of water vapor and other volatile compounds might be significant in these exoplanets, contributing to the low densities observed. The combination of hydrogen-rich atmospheres along with substantial amounts of water can lead to different phases of cloud formation and weather patterns that are less characteristic of denser rocky planets. This unique mixture can create intriguing weather systems and atmospheric conditions, which are still being studied to understand their impacts over long periods. The formation and evolutionary history of these cotton candy worlds could also provide clues into the processes that led to their current state. Perhaps they formed in more massive protoplanetary disks or were once closer to their host stars and later migrated outward, allowing them to accumulate lighter gases without the intense heat that would otherwise strip them away. This captivating aspect of planetary formation challenges our understanding of what constitutes a planet and hints at the diverse possibilities waiting to be discovered in distant star systems. Exoplanets that maintain stable orbits around pulsars do so under a set of unique conditions shaped by the characteristics of pulsars themselves. Pulsars are highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation. Their extreme density and magnetic fields create powerful gravitational forces that can influence the orbits of nearby objects, including planets. Understanding how exoplanets adapt to these challenging environments reveals a fascinating aspect of planetary stability. For an exoplanet to maintain a stable orbit around a pulsar, it must reside at an optimal distance, known as the habitable zone or gravitational sweet spot. This distance balances the gravitational pull from the pulsar against the planet's orbital speed, ensuring that the planet is neither pulled in too closely nor flung away into space. The intense radiation emitted by pulsars can also present hazards, but some exoplanets have demonstrated resistance to these forces by having sufficiently strong magnetic fields or protective atmospheres. Additionally, the formation of planets around pulsars is often thought to occur in the aftermath of a supernova explosion, which leaves behind a pulsar. The surrounding debris can provide a reservoir of material for forming planets. As planets coalesce from this material, they can establish stable orbital paths early on, securing their position around the pulsar. The remaining debris can create an environment where subsequent collisions and gravitational interactions may be less frequent, allowing for more stable orbits. Moreover, observations have revealed that many pulsars have been found to host planets in carefully measured orbital configurations. These arrangements can also be influenced by the pulsar's rotational characteristics, such as its spin rate and magnetic field orientation. As a result, planets that find themselves in the right orbital paths can thrive, adapting to the pulsar's unique environment while revealing the impressive nature of planetary diversity in the universe. The presence of wildly elliptical orbits in some exoplanets can often be attributed to a combination of gravitational interactions, chaotic dynamics, and evolutionary history. When planets form within protoplanetary disks, their initial orbits can be relatively circular. However, over time, various forces can act on them, shaping their orbits into elongated paths that take them far from their host stars at certain intervals. One significant factor is the gravitational influence of other celestial bodies in the system. When multiple planets exist close to each other, their gravitational interactions can lead to complex orbital changes. If one planet gets too close to another during its orbit, this can result in a gravitational slingshot effect, altering the paths of both bodies. These interactions can push planets into more eccentric orbits, causing them to exhibit the elongated shapes that characterize their new trajectories. Another influential factor involves the migration of planets. Many exoplanets start their lives further from their stars and gradually spiral inward over time due to interactions with the protoplanetary disk or other planets. This migration can result in highly elliptical orbits, especially if the planets encounter resonances that amplify their orbital eccentricity. Such resonance occurs when two orbiting bodies exert regular, periodic gravitational influence on each other, typically enhancing their elliptical paths. Lastly, stellar influences also play a vital role in shaping exoplanet orbits. Close encounters with neighboring stars can perturb a planet's orbit, causing significant changes in its trajectory. If a planet comes close enough to another star, the gravitational forces can stretch its orbit from a circular to a highly elliptical one. These encounters and interactions create a dynamic astronomical ballet, illustrating a fascinating interplay of forces that govern the orbits of exoplanets throughout their lifespans. In the first fraction of a second after the Big Bang, the universe underwent a series of rapid and transformative events that set the stage for everything that followed. This period is known as the Planck epoch, during which the universe was extremely hot and dense, existing at temperatures greater than 10 to the power of 27 degrees Kelvin. The fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were unified in a single force during this brief moment. As the universe began to cool, it quickly transitioned beyond the Planck epoch into the Grand Unification epoch. During this time, the fundamental forces started to separate, with gravity differentiating from the other forces. The universe expanded rapidly in a process known as cosmic inflation, which lasted for a fraction of a second, exponentially stretching space and smoothing out any irregularities. This inflationary phase allowed different regions of the universe to traverse far apart, even as they shared the same initial conditions. As inflation ended, the universe continued to cool and matter began to form. In the next stage, known as reheating, energy from inflation converted into particle-antiparticle pairs, leading to the creation of a variety of fundamental particles, including quarks, electrons, and neutrinos. Conditions remained so energetic that these particles could not yet form stable atoms, maintaining a soup-like state of free particles. By approximately 1 second after the Big Bang, the universe had expanded and cooled enough for quarks to combine in 2s and 3s, forming protons and neutrons. This marked the beginning of the baryogenesis phase, where the matter that would eventually lead to stars and galaxies started its journey from this explosive origin. Understanding these early moments reveals the foundation of our universe, explaining not only how it formed but also why it took the shape we observe today. The formation of the first stars and galaxies in the early universe marks a pivotal moment in cosmic history, often referred to as the cosmic dawn. This process began after the universe underwent a period of cooling and expanding following the Big Bang, which took place about 380,000 years after the initial explosion. At this point, the universe had cooled enough for electrons to combine with protons, forming neutral hydrogen atoms in a phase known as recombination. This led to a dark era as the universe became mostly transparent to radiation. As the universe continued to expand, small fluctuations in the density of matter, left over from the quantum fluctuations during inflation, played a crucial role in initiating star and galaxy formation. Regions of slightly higher density began to gravitationally attract surrounding gas, primarily composed of hydrogen and helium. Over millions of years, these dense regions collapsed under their own gravity, forming the first cosmic structures. Once the density reached a critical threshold, these clumps of gas formed protostars, leading to regions where matter gathered and heated up. As the gravitational pressure intensified, temperatures soared within these protostars, eventually reaching the conditions necessary for nuclear fusion. This process ignited the first stars, often referred to as population 3 stars. These early stars were massive and short-lived, burning through their fuel rapidly and producing vast amounts of energy, which contributed to the ionization of the universe. The intense radiation and stellar winds from these first stars had a tremendous impact on their surroundings, helping to clear out large amounts of gas and dust, facilitating the formation of galaxies. These star clusters began to merge and evolve into larger structures, creating the framework for the galaxies we observe today. The interplay between gravity, radiation, and cosmic evolution set the stage for the rich tapestry of galaxies that fill our universe. Through this intricate process, the initial seeds of cosmic structure laid the foundation for everything from our own Milky Way to the countless other galaxies scattered throughout the vastness of space. Dark matter is a mysterious component of the universe that is believed to account for approximately 25% of its total mass energy content. Unlike normal matter, which makes up stars, planets, and all living things, dark matter does not emit, absorb, or reflect any electromagnetic radiation, such as light. This makes it invisible and detectable only through its gravitational effects on visible matter and radiation. The existence of dark matter has been inferred from various astrophysical observations, such as the way galaxies rotate and how galaxy clusters behave under gravitational influences. One key observation indicating the presence of dark matter is the rotational speeds of galaxies. According to Newtonian physics, the outer regions of galaxies should rotate more slowly than their inner regions due to the distribution of visible mass. However, astronomers have found that the outer parts of galaxies rotate at unexpectedly high speeds, suggesting the presence of significant amounts of unseen mass, now identified as dark matter. Similarly, gravitational lensing, the bending of light from distant objects around massive clusters of galaxies, provides another way we can infer the presence of dark matter. The lensing effect is stronger than what would be expected based solely on visible matter, indicating that there is much more mass present than what is visible. Dark matter interacts with regular matter primarily through gravity, but its exact nature remains elusive. Many theoretical candidates for dark matter include weakly interacting massive particles, or WIMPs, which would interact through the weak nuclear force in addition to gravity. Other candidates could include axions or sterile neutrinos, but none have been definitively detected. Because dark matter does not interact electromagnetically, it does not form atoms or molecules, making it fundamentally different from the matter that makes up stars, planets, and living organisms. Research is ongoing to explore the fundamental properties of dark matter and its potential interactions beyond gravity. Experiments designed to detect dark matter particles directly or indirectly are being conducted deep underground or in space, yet none have yielded conclusive results thus far. Understanding the nature of dark matter is crucial because it plays a vital role in the formation and evolution of structures in the universe, influencing how galaxies and galaxy clusters develop over time. The quest to uncover what dark matter is represents one of the most significant challenges in modern astrophysics and cosmology. The apparent predominance of matter over antimatter in the universe is one of the great mysteries of modern physics and cosmology. According to the fundamental laws of physics, for every particle of matter, an equivalent antiparticle should exist. When matter and antimatter meet, they annihilate each other, producing energy in the form of photons. During the early moments after the Big Bang, both matter and antimatter should have emerged in roughly equal amounts, but our observable universe is predominantly composed of matter, with very little antimatter detected. This imbalance is explained through a phenomenon known as baryon asymmetry. Theories suggest that during the extremely hot and dense conditions of the early universe, processes might have favored the production of matter over antimatter. One leading explanation involves a term called CP violation, which refers to violations of the combined symmetry of charge conjugation and parity. In certain particle decays, experiments have shown that particles decay differently from their antiparticle counterparts, hinting at an asymmetry in how matter and antimatter behave under specific conditions. Several models propose various mechanisms that could have led to this asymmetry. One of the most notable is electroweak baryogenesis, which suggests that at high energies, interactions involving the electroweak force, one of the fundamental forces of nature, could have produced an imbalance between matter and antimatter. Another possibility involves certain theoretical particles such as the Higgs boson, which may play a role in preferentially generating matter. Ultimately, the exact process that led to the excess of matter over antimatter remains unresolved. Researchers continue to explore this question through experiments looking for signs of baryon asymmetry and particle collisions, cosmic background radiation, and other cosmological phenomena. Investigating this matter-antimatter imbalance not only deepens our understanding of particle physics, but also addresses fundamental questions about the universe's origins and the conditions that enabled its evolution as we perceive it today. The answers may hold the keys to understanding the fundamental structure of reality itself. Cosmic inflation refers to the rapid exponential expansion of the universe that occurred in the first moments after the Big Bang, roughly between 10 to the power of -36 and 10 to the power of -32 seconds. This remarkable phase of inflation helps explain several features of our universe, including its uniformity and the distribution of cosmic structures. While the exact cause of cosmic inflation remains an area of active research, there are several leading theories that provide potential mechanisms for this dramatic expansion. One prominent hypothesis suggests that inflation was driven by a scalar field known as the inflaton field. This hypothetical field is believed to have occupied the early universe and produced negative pressure, which in turn led to a rapid expansion of space itself. As the inflaton field decayed, it converted its energy into particles and radiation, leading to the universe's subsequent cooling and the formation of the cosmic structures we observe today. This process can be likened to a release of pent-up energy that propels the universe into a period of accelerated growth. Another aspect of cosmic inflation is how it addresses specific puzzles in cosmology, such as the flatness problem and the horizon problem. The flatness problem concerns the precise balance of density in the universe. Inflation explains why our universe appears so flat today by stretching minor fluctuations from a highly curved state to a flat geometry. The horizon problem highlights the homogeneous temperature of the cosmic microwave background radiation across vast distances, even regions that should not have been in contact with each other. Inflation allows for these regions to have once been in close proximity before rapid expansion separated them. In addition to these theoretical frameworks, researchers are actively testing the predictions of inflationary models through observational data, such as measurements from cosmic microwave background radiation and large-scale structure surveys. While the exact mechanisms behind cosmic inflation are still being explored, the concept has fundamentally advanced our understanding of the early universe and the processes that led to the cosmos as we experience it today. This foundational phase of inflation not only reshaped the universe in its infancy, but also laid the groundwork for the formation of galaxies, stars, and ultimately, life itself. The fate of the universe is a subject of considerable speculation and research within cosmology, and three primary scenarios have emerged regarding how it might ultimately end: the Big Freeze, the Big Rip, and the Big Crunch. Each of these scenarios depends on the dynamics of cosmic expansion, the density of matter, and the properties of dark energy, which is thought to drive the accelerated expansion of the universe. The Big Freeze is currently the most widely accepted model according to our observations of the universe. In this scenario, the universe continues to expand indefinitely, stretching the cosmos ever further apart. Over immense timescales, trillions of years, galaxies will drift away from each other, leading to an increasingly cold and empty universe. Star formation will cease as the available gas and dust are exhausted, leaving behind only remnants like white dwarfs, neutron stars, and black holes. Eventually, all stars will burn out, and the universe will reach a state of thermodynamic equilibrium filled mostly with low-energy radiation and dark matter, resembling a heat death. This long, slow decline is characterized by a universe that becomes dark and cold. Contrastingly, the Big Rip posits a more dramatic conclusion. If dark energy were to increase in strength over time, it could exert a force that ultimately overwhelms the gravitational bindings of galaxies, stars, and even planetary systems. In this scenario, the accelerated expansion accelerates to a point where it tears apart galaxies, stars, planets, and eventually even atomic structures. The universe would end with a catastrophic disintegration of everything into an infinitesimal state, leading to a chaotic and unrecognizable cosmos. The Big Crunch presents yet another possibility. In this model, the expansion of the universe eventually slows due to gravitational forces, leading to a reversal of cosmic expansion. The universe would then contract, pulling galaxies closer together until they collide and merge into an increasingly dense state. As this process continues, the temperature of the universe would rise dramatically, culminating in an incredibly hot and dense singularity, reminiscent of the conditions present at the Big Bang. This cyclic view of the universe implies a potential rebirth, as the cosmos could, theoretically, re-enter an expansion phase after collapsing. Current observations, including the measurement of cosmic acceleration and dark energy's influence, lean toward the Big Freeze as the most probable outcome. However, as research continues and new cosmic phenomena are uncovered, our understanding of the universe's fate may evolve, providing deeper insights into the ultimate destiny of all existence. Each scenario incorporates fascinating aspects of physics that not only explain the distant future of the universe, but also deepen our comprehension of space, time, and the fundamental forces at play. The concept of a multiverse suggests that our universe may be just one of many distinct universes that exist simultaneously, each with potentially different physical laws, constants, and properties. While the notion of a multiverse has gained traction in certain areas of theoretical physics and cosmology, it remains largely speculative and is an area of intense debate among scientists. There is no definitive experimental evidence confirming the existence of multiple universes, which makes it a fascinating but unresolved question in modern science. Several theoretical frameworks propose various types of multiverses. One example is the inflationary multiverse, which arises from the theory of cosmic inflation. According to this idea, as the universe underwent rapid expansion in its infancy, different regions could stop inflating at different times, resulting in bubble universes. Each bubble may have its own distinct properties, and these bubbles can represent different universes within a larger multiverse. In this scenario, there might be an infinite number of universes, each with variations in their physical laws and constants. Another concept is the many worlds interpretation of quantum mechanics, which posits that every quantum event results in the branching of universes. In this interpretation, all possible outcomes of quantum measurements actually occur, each in its own separate universe. This suggests a vast landscape of universes that includes every conceivable variation of outcomes from quantum events. The total number of universes in a multiverse scenario is an open question and can range from a countable infinity to an unbounded number beyond comprehension. Some models even suggest that universes can continuously form and dissolve, further complicating the idea of counting them in any traditional sense. The implication is that if a multiverse exists, our understanding of reality as we know it might be fundamentally limited. While the multiverse idea provides intriguing possibilities and elegantly explains certain phenomena within theoretical frameworks, it also raises significant philosophical and scientific questions. Testing the multiverse hypothesis directly is challenging because other universes would likely be inaccessible to us based on our current understanding of physics. Thus, while the concept of living in a multiverse continues to inspire thinking and discussion, it remains an area rich with potential but lacking definitive empirical evidence. Quantum entanglement is a remarkable phenomenon that arises from the principles of quantum mechanics, where two or more particles become interconnected in such a way that the state of one particle instantaneously influences the state of the other, regardless of the distance separating them. This phenomenon challenges our classical intuitions about how particles interact, and has led to deep questions about the nature of reality, space, and time. When particles are entangled, measuring the state of one particle directly affects the state of the other, even if they are light years apart. This phenomenon was famously described by Albert Einstein as spooky action at a distance. Einstein, along with his colleagues, initially viewed this entanglement as problematic for a local understanding of physics. However, numerous experiments, starting with those of Alain Aspect in the early 1800s, have confirmed that entangled particles do indeed display this instantaneous correlation, regardless of the spatial separation. The exact mechanism behind this instantaneous connection remains one of the biggest mysteries in quantum mechanics. The implications of quantum entanglement for our understanding of space-time are profound. Entanglement suggests a non-locality that defies the classical notion that information cannot travel faster than the speed of light. This has led to reconsiderations of how scientists understand the structure of space and time. Some interpretations propose that entangled particles could indicate a deeper interconnectedness of the universe, challenging the idea that space-time is fundamentally separate and distinct for every individual particle. Additionally, quantum entanglement plays a significant role in emerging theories of quantum gravity, where physicists seek to unify general relativity with quantum mechanics. Some researchers have speculated that space-time itself might emerge from the entanglement relationships of fundamental quantum particles. In this view, the fabric of the universe could be woven from the entanglement connections among particles, suggesting that what we perceive as space-time could be an emergent property of these underlying quantum states. Researchers continue to explore the implications and mysteries of quantum entanglement through various experiments and theoretical advancements. Its connections to foundational concepts in physics not only redefine our understanding of the quantum realm, but also challenge existing paradigms about how we conceptualize reality itself. As scientists probe deeper into the intricacies of entanglement, they may uncover insights that could reshape our understanding of the universe at the most fundamental level. Primordial black holes are a fascinating class of black holes that are hypothesized to have formed in the very early universe, shortly after the Big Bang. Unlike stellar black holes, which form from the gravitational collapse of massive stars at the end of their life cycles, primordial black holes could have emerged from density fluctuations in the hot, dense environment of the early universe. As the universe expanded and cooled, regions of space with higher than average density could have collapsed under their own gravity, resulting in the formation of these black holes. The conditions that prevailed in the early universe were extreme, with high energy densities and rapid expansion during the inflationary era. During this time, quantum fluctuations could have been amplified to macroscopic scales, leading to significant variations in density throughout the primordial cosmic soup. If some of these fluctuations reached sufficient critical density, they could have undergone gravitational collapse, forming black holes before stars, galaxies, or other large structures had a chance to develop. This mechanism allows for the possibility of primordial black holes with a wide range of masses, from very tiny ones, perhaps only a few times the mass of a small asteroid, to much larger black holes. Primordial black holes might play a unique role in the evolution of the universe. For one, they could act as seeds for the formation of galaxies and large-scale structures. Their gravitational influence could have drawn in surrounding matter, promoting galactic formation processes. This aspect brings intriguing questions about how these black holes might interact with the matter around them and impact cosmic evolution. Additionally, there has been speculation about the connection between primordial black holes and dark matter. Some theories propose that these black holes could constitute a portion, or even all, of the dark matter that permeates the universe. This hypothesis is intriguing because it could provide insights into the elusive nature of dark matter, which is currently understood primarily through its gravitational effects on visible matter. The quest to understand primordial black holes encompasses ongoing observational efforts, including studies of gravitational waves and searches for potential signatures of these black holes within cosmic structures. These investigations could lead to breakthroughs in our understanding of the early universe, black hole formation processes, and the role they play in shaping the cosmos we observe today. As researchers continue to explore these enigmatic objects, primordial black holes open up a rich area of inquiry at the intersection of cosmology, astrophysics, and fundamental physics. The cold spot in the cosmic microwave background radiation, which is a remnant of the Big Bang, presents a fascinating puzzle for scientists. This particular region is notably cooler than its surrounding areas, presenting temperatures that are slightly below average. One of the leading theories to explain this phenomenon is the possibility of a large supervoid, a vast area of space with significantly fewer galaxies than the average. If such a supervoid exists, it could stretch across millions of light years and would have less matter to contribute to the gravitational influences that regulate temperatures. Another intriguing hypothesis considers the possibility of primordial fluctuations in the density of matter in the early universe. These fluctuations would have influenced the formation of cosmic structures and might have led to variations in temperature across the cosmic microwave background. Some researchers speculate that the cold spot could be the result of an unusual cosmic event or the remnants of an ancient supercluster's gravitational influence that has left a mark on the fabric of space-time. Additionally, there's a theory that explores the implications of other universes. Speculation around the multiverse suggests that our universe may be just one of many. If another universe collided with ours, it might create disturbances in the cosmic microwave background, potentially manifesting as cold or hot spots. This concept pushes the boundaries of our understanding and invites further research and exploration. As scientists continue to investigate the cold spot, it reminds us of the universe's complexity and the challenges we face in piecing together its history. Each discovery not only helps to illuminate the origins of our cosmos, but also raises deeper questions about the nature of reality itself. The WOW signal, detected on August 15, 1977, is one of the most intriguing events in the search for extraterrestrial intelligence. This strong radio signal came from the direction of the constellation Sagittarius and lasted for 72 seconds. It was recorded by a radio telescope at Ohio State University, and the intensity of the signal was so remarkable that one of the astronomers, Jerry R. Amon, wrote the word WOW in red ink on the printout, giving the signal its memorable name. What makes the WOW signal particularly fascinating is that it matched the expected signature of a signal that could be produced by an alien civilization. It had the right frequency, falling in the range of hydrogen, a key element in the universe, and a frequency commonly monitored in the search for extraterrestrial messages. Despite subsequent investigations, the signal has never been definitively repeated or traced back to a specific source, leaving a cloud of mystery surrounding its origin. Several theories have been proposed to explain the signal. Some suggest it may have been a natural phenomenon, possibly related to a comet or another astronomical event. However, these theories struggle to account for the narrow bandwidth and the unique properties of the signal that align closely with artificial origins. Others speculate it could have been a transmission from an extraterrestrial source, representing an advanced civilization attempting to communicate across the vast distances of space. The lack of a clear explanation for the WOW signal ignites the imagination and fuels ongoing discussions within the scientific community. As technology advances and our understanding of the universe expands, the mystery of the WOW signal continues to challenge researchers to explore the vast possibilities of life beyond our planet. It stands as a reminder of how much we have yet to uncover about our universe and the potential neighbors waiting to be discovered. The formation of organic molecules on Mars is an area of great interest for scientists, particularly in the search for past life on the planet. Organic molecules are the building blocks of life as we know it, composed primarily of carbon, and can include a variety of other elements such as hydrogen, oxygen, and nitrogen. Evidence suggests that these molecules may have formed through a combination of processes, both biological and abiotic, during Mars's ancient history. One significant source of organic molecules comes from the planet's geology. Mars is known to have once had a wetter, warmer climate with conditions that might have allowed for chemical reactions to occur, possibly leading to the creation of simple organic compounds. Laboratory experiments have demonstrated that under the right conditions, such as those found in hydrothermal systems or in the presence of specific minerals, organic molecules can form. These reactions could have taken place in the Martian soil or in subsurface habitats. In addition to geological processes, the detection of organic molecules by missions such as the Curiosity rover has raised intriguing possibilities. Curiosity discovered complex organic compounds in sedimentary rocks, suggesting that if life ever existed on Mars, there could be remnants of it within these molecules. However, these organic compounds can also arise from non-biological processes, such as the interaction of carbon-rich materials with UV radiation or cosmic rays and thermal events. While the presence of organic molecules hints at the planet's potential for past life, they do not serve as conclusive evidence. The exciting notion lies in understanding whether these molecules could be remnants of ancient biological activity or simply the result of natural chemistry. Future missions, such as the Mars Sample Return mission, aim to collect samples and return them to Earth for deeper analysis. This would provide essential insights into the question of whether life ever thrived on Mars, enriching our understanding of the planet's history and the broader search for life elsewhere in the universe. Astronauts have reported experiencing mysterious flashes of light during missions in space, a phenomenon that has puzzled scientists and captured public fascination. These flashes often occur in the dark, such as during spacewalks or when passing through the Earth's shadow. While they can be startling, they are believed to be a result of cosmic rays interacting with the human eye. Cosmic rays are high-energy particles, mostly protons, that travel through space and are a natural part of the cosmic environment. These particles originate from various sources, including supernovae and the Sun itself. When cosmic rays enter the protective environment of the spacecraft or spacecraft suit, they can collide with the atoms in the astronaut's eyes, producing a cascade of secondary particles. This interaction can trigger a response in the retina, creating the perception of a flash or streak of light. The phenomenon is akin to the visual experiences of people undergoing a medical procedure called a retinal scan, in which a direct impact on the retina can create similar flashes, even without actual light. Furthermore, the lack of atmosphere in space means that there are no particles or air to scatter the light in the same way they do on Earth, making these flashes particularly noticeable to astronauts. Research into this phenomenon has advanced our understanding of the hazards associated with space travel. The frequent exposure to cosmic rays can contribute to longer-term health risks, including increased rates of cancer and potential damage to the nervous system. As space exploration continues, astronauts will need to remain vigilant about these flashes and understand their implications on their health and performance during missions, especially on long-duration voyages to destinations like Mars. This ongoing investigation not only unveils the mysteries of human experience in space, but also highlights the challenges faced by explorers venturing beyond our planet. As we prepare for more ambitious missions, understanding these flashes and cosmic rays will be essential for safeguarding the well-being of astronauts. The presence of water on the Moon has intrigued scientists for decades, and recent research has helped to unravel the complex history of how this vital resource may have formed or arrived on our celestial neighbor. One of the leading theories suggests that water was delivered to the Moon by comets and asteroids that collided with its surface. These icy bodies, rich in water, impacted the Moon over billions of years and released their water content upon collision. Another possibility is that water existed as a part of the Moon's formation process itself. The Moon formed about 4.5 billion years ago, likely from debris resulting from a colossal impact between the young Earth and a Mars-sized body. During this chaotic time, water in the form of vapor could have been trapped within the Moon's molten material. As the Moon cooled, some of this water would have been released, potentially leading to pockets of water ice in permanently shadowed regions. Recent missions to the Moon, including those by NASA's Lunar Reconnaissance Orbiter and India's Chandrayaan-1, have detected water ice in significant quantities at the lunar poles, specifically in areas that never see sunlight. Some estimates suggest that there could be millions of tons of water ice locked in these permanently shadowed craters. This ice represents a vital resource for future lunar exploration, as water can be split into hydrogen and oxygen, providing breathable air and propellant for spacecraft. Understanding the origins and quantity of water on the Moon not only enriches our knowledge of its geological history, but also has profound implications for human exploration. With plans for missions to establish a sustainable presence on the Moon, particularly under NASA's Artemis program, tapping into lunar resources like water could be essential for long-term habitation and further journeys to Mars and beyond. The Moon's water may be more than just a curiosity, it could be a key to our future in space. The Trojan asteroid designated 2010 TK7 is a fascinating object that orbits the Sun in a stable position relative to Earth. Trojans are asteroids that share an orbit with a larger planet, positioned at specific points known as Lagrange points. In the case of 2010 TK7, it resides at the Earth's first Lagrange point, which is located approximately 150,000 kilometers ahead of Earth in its orbit. The origin of Trojan asteroids like 2010 TK7 is believed to be linked to the early history of our solar system. During the formation of the planets, billions of years ago, the solar system was a chaotic place filled with numerous small bodies. Some of these objects were trapped in stable orbits, managing to avoid collisions as the planets coalesced into their current forms. As a result, these bodies could have been nudged into their current positions by gravitational interactions with larger bodies, including the early Earth and other planetary neighbors. Identifying the exact origin of individual Trojan asteroids can be challenging. However, many scientists believe that they may be remnants of the primordial material that formed the planets. Some studies suggest that they could be made up of the same materials as the outer planets, or could represent fragments from larger bodies that were broken apart during collisions. This connection to the early solar system makes objects like 2010 TK7 valuable for understanding the conditions that existed at that time. The prospect of studying Trojan asteroids also holds significant promise for future space exploration. As the field of planetary science evolves, missions to these stable points in space could provide insights into the building blocks of our solar system and the processes that shape the planets, potentially revealing secrets about the very origins of Earth itself. The study of such asteroids enriches our understanding of the dynamic nature of our celestial neighborhood and the intricate dance of forces that govern it. Enceladus, one of Saturn's intriguing moons, captivates scientists with its spectacular geysers that erupt from its south pole. The source of this geological activity is deeply tied to the moon's internal structure and the presence of a subsurface ocean. Beneath its icy exterior lies a global ocean of liquid water, heated by tidal forces generated by the gravitational pull of Saturn and its other moons. The phenomenon of geysers is primarily driven by the complex interplay of heat and pressure. As Saturn's strong gravitational forces flex and stretch Enceladus, tidal heating occurs. This frictional heat keeps the water beneath the icy crust in a liquid state, even though the surface temperatures are extremely cold. The combination of this liquid water, along with various dissolved salts and organic materials, creates a dynamic environment that fosters geyser activity. The geysers themselves are found in a region known as the Tiger Stripes, which are fractures in the moon's icy surface. These fractures allow the pressurized subsurface ocean to escape. When the pressure builds up sufficiently, the water vapor and ice particles erupt into space, creating plumes that can reach several hundred kilometers above the surface. These geysers not only illuminate the active geological state of Enceladus, but also provide invaluable information about the ocean beneath. The study of these geysers has significant implications for our understanding of the potential for life beyond Earth. The presence of liquid water, along with organic compounds, raises the exciting possibility that Enceladus could harbor microbial life in its hidden ocean. Future missions to Enceladus aim to analyze the composition of the geyser plumes, further exploring this moon as a key candidate in the search for extraterrestrial life within our solar system. Each discovery contributes to the unfolding story of this captivating moon and its hidden wonders beneath the icy surface. Mysterious fluctuations in the levels of oxygen in Mars's atmosphere have intrigued scientists and raised questions about the processes occurring on the red planet. Observations have shown that the concentration of oxygen can vary dramatically, fluctuating by as much as 30% over a seasonal cycle. Understanding these changes is critical for unraveling Mars' environmental dynamics and the potential for past or present life. One of the primary explanations for these oxygen fluctuations centers on the seasonal changes in temperature and atmospheric pressure on Mars. During the Martian winter, carbon dioxide freezes at the polar ice caps, leading to a decrease in atmospheric pressure. As the carbon dioxide sublimates back into gas during the warmer months, it can push other gases, such as oxygen, to varying concentrations. the sublimation and deposition processes of carbon dioxide may indirectly influence the behavior and availability of oxygen in the atmosphere. Additionally, researchers have considered the role of chemical reactions occurring on the Martian surface and in the atmosphere itself. For example, the interaction of solar radiation with various surface minerals can lead to photochemical reactions that produce oxygen. The presence of catalyzing materials like iron oxides in the regolith might also contribute to the cycling of oxygen through various chemical processes. While natural processes are likely responsible for most of these fluctuations, some scientists speculate about the possibility of biological activity. However, there is currently no direct evidence to support this notion. As Mission Mars continues to explore the planet, analyses of the atmospheric composition and ongoing studies of Martian soil and surface will deepen our understanding of these oxygen fluctuations. Such insights could give us a clearer picture of Mars's climatic history and its potential habitability. Each discovery adds another piece to the puzzle of our neighboring planet, reaffirming the importance of ongoing exploration in the quest to understand the nature of Mars and its atmosphere. The peculiar shapes of asteroids like Bennu are the result of a combination of their formation processes and their subsequent evolution over billions of years. Bennu, which is classified as a near-Earth asteroid, has a distinctive boulder-like rubble pile structure that sets it apart from more solid celestial bodies. This unique shape can be traced back to the way these objects formed in the early solar system. Bennu and similar asteroids are thought to have originated from larger parent bodies that experienced catastrophic collisions. When larger asteroids collided, they would break apart, creating smaller fragments. Over time, the gravitational attraction between these fragments allowed them to come together, but the lack of sufficient mass and gravity meant that they did not coalesce into solid bodies like planets. Instead, they formed what we refer to as rubble piles, a collection of loosely bound rocks and debris, allowing for irregular shapes. The gravitational force acting on these asteroid aggregates is quite weak compared to larger bodies, which results in their unusual shapes. As a result of this low gravitational pull, various factors such as rotation can influence how they appear. For example, Bennu rotates once approximately every 4 hours, which causes its equatorial region to bulge slightly, contributing to its overall shape, often described as resembling a spinning top. In addition to gravitational influences, external factors such as impacts with other smaller bodies can also reshape asteroids over time. The craters and grooves seen on Bennu's surface were formed by such impacts, which add complexity to its appearance. Exploring asteroids like Bennu provides not only insights into their unique shapes, but also sheds light on the processes that governed the early solar system. Studying these objects enables scientists to understand the building blocks of planets and the potential for finding organic material or water within these ancient remnants. The subsurface oceans found on various moons in our solar system present some of the most intriguing possibilities for extraterrestrial life. These oceans, hidden beneath thick layers of ice or rock, are believed to be the result of interactions between heat sources, the gravitational influences of nearby celestial bodies, and the unique geological conditions present on these moons. One of the most well-known examples is Europa, a moon of Jupiter. It is believed to harbor a vast ocean beneath its icy crust, with estimates suggesting it could be up to 150 kilometers deep. Tidal heating, caused by the gravitational pull from Jupiter and its other moons, keeps the ocean in a liquid state despite the extremely low surface temperatures. The potential for organic materials and the chemical energy produced by interactions between the ocean and the moon's rocky mantle raises exciting prospects for the existence of life in Europa's ocean. Another fascinating case is Enceladus, one of Saturn's moons. Its subsurface ocean is similarly kept warm by tidal heating, and geysers erupting from its south pole vent water vapor and ice particles into space. The plumes contain organic compounds and dissolved salts, providing tantalizing evidence of the ocean's chemistry. Like Europa, Enceladus presents a strong candidate for habitability, as the conditions may support microbial life in its hidden ocean. Ganymede, another of Jupiter's moons, also possesses a subsurface ocean beneath its icy exterior. Recent measurements suggest that Ganymede's ocean may be sandwiched between layers of ice and could be even deeper than Europa's. This moon is unique in that it has its own magnetic field, hinting at complex geological activity that may play a role in the dynamics of its ocean. Finally, Titan, Saturn's largest moon, displays a different but equally fascinating context. Titan has large liquid methane and ethane lakes on its surface, but beneath its icy shell, there might be a subsurface ocean of water mixed with ammonia. This combination creates a radically different environment that could harbor life forms adapted to such unique conditions. These subsurface oceans provide compelling targets for future exploration, as studying them could yield insights into not only the moons themselves, but also the broader question of life's existence beyond Earth. The diverse environments and geological processes at play offer a rich tapestry for understanding the origins and adaptability of life in the universe. Titan, Saturn's largest moon, presents a striking resemblance to Earth in terms of its complex surface features and geological processes, despite having a composition and atmosphere that differ significantly from our planet. This similarity can largely be attributed to the presence of a thick atmosphere and the unique conditions created by its extremely low temperatures. Titan's atmosphere is predominantly composed of nitrogen, similar to Earth's, but it also contains a significant amount of methane. This unique combination allows for a rich chemical environment that leads to the formation of clouds, precipitation, and even bodies of liquid on the surface. The presence of methane lakes and rivers creates features reminiscent of terrestrial landscapes, including coastlines and deltas. These hydrocarbons serve as a natural analogue to Earth's water cycle, where liquid methane evaporates, condenses, and precipitates, shaping the landscape in ways that mirror our own hydrological processes. The cold temperatures on Titan, which hover around -180 degrees Celsius, create a scenario where methane exists as a liquid, allowing for erosion, sediment transport, and other geological processes. Titan's surface conditions facilitate the interaction of ice and hydrocarbon, leading to features like cryovolcanoes that erupt with slushy mixtures of water and ammonia instead of molten rock. These processes contribute to a dynamic environment, enabling Titan to exhibit a range of geological characteristics similar to those found on Earth. Moreover, Titan's atmosphere plays a crucial role in shaping its surface. The presence of wind and weather systems creates complex terrains, including sand dunes that resemble those found in deserts on Earth. The interactions between the thick atmosphere and surface materials lead to an ever-evolving landscape, showcasing a dynamic geology driven by the same fundamental processes observed on our planet. The study of Titan provides valuable insights into the potential for similar Earth-like processes elsewhere in the universe, even in environments that may appear alien at first glance. By understanding this moon's features, scientists gain a deeper appreciation for the diverse possibilities of planetary formations and the conditions under which geological and potentially prebiotic processes can occur, challenging our assumptions about habitability and life in extreme environments. The periodic dimming of stars in the Crab Nebula is primarily caused by the presence of a neutron star at its center, commonly known as the Crab pulsar. This pulsar is a highly magnetized, rotating neutron star that emits beams of electromagnetic radiation from its magnetic poles. As the pulsar spins, these beams sweep across space much like a lighthouse beam, which creates the phenomenon of periodic dimming, or pulsation, as viewed from Earth. As the pulsar rotates, it produces intense bursts of radiation across a range of wavelengths, including radio, optical, and X-ray emissions. When the beam of radiation is directed toward Earth, the star appears to brighten. When the beam rotates away, the star dims. This periodicity is incredibly precise, with the Crab pulsar completing one rotation approximately every 33 milliseconds. The regularity of this pulsing effect is one of the fascinating characteristics of pulsars and provides important information about the stellar remnant's rotation and magnetic field. The environment around the pulsar is also significant. The Crab Nebula itself is the result of the supernova explosion that produced the pulsar in the year 905 AD. As the expanding debris from the supernova interacts with the pulsar's magnetic field, it creates a complex structure of shocks and emission across different wavelengths. This interaction generates additional radiation, contributing to the observable changes in brightness associated with the periodic dimming. The study of the periodic dimming in the Crab Nebula, primarily driven by the pulsar's activity, not only enhances our understanding of the life cycle of stars, but also provides insights into the physics of neutron stars and the extreme conditions present in their vicinity. Pulsars like the Crab provide a natural laboratory for studying fundamental questions in astrophysics, contributing to our understanding of the universe's behavior and the life cycles of celestial bodies. The phenomenon where some stars appear older than the universe itself is a delightful conundrum in astrophysics that arises from various factors related to stellar formation and measurement. The observable universe is estimated to be around 13.8 billion years old, based on the cosmic microwave background radiation and other cosmological evidence. When astronomers observe certain stars that seem to have ages exceeding this time frame, it suggests a deeper look into the intricacies of stellar evolution and the complexities in age estimation. One of the primary reasons for these apparent age discrepancies is linked to the methods used to determine a star's age. Astronomers often estimate stellar ages based on the star's position on the Hertzsprung-Russell diagram, which plots stars according to their brightness and temperature. However, this method can lead to uncertainties, especially for stars in the later stages of evolution. If a star is found in a part of the diagram that implies a much older age, it may not accurately reflect its true age if the underlying assumptions about evolutionary processes are flawed or incomplete. Another factor contributing to this paradox is the nature of the star's composition. Stars with higher concentrations of heavy elements, known as metals in astronomical terms, usually form after previous generations of stars evolved and died, enriching the interstellar medium. Therefore, a star with a low metallicity could indicate that it was born from primordial materials, suggesting that it has existed since the early universe. Nonetheless, these lower metallicity stars might appear older than they truly are due to the complexities of stellar dynamics and life cycles. Additionally, some stars are part of globular clusters, which are densely packed collections of ancient stars. The ages of these clusters can be difficult to determine accurately. Often, the oldest globular clusters are estimated to be nearly 14 billion years old based on stellar models, causing them to seemingly push against the upper limits of the universe's age. This overlap raises questions about the very models we use to estimate stellar ages and the history of star formation in the cosmos. In conclusion, the apparent older ages of certain stars challenge our understanding of stellar evolution and highlight the need for refining our modeling techniques. As researchers continue to explore these celestial objects with advanced telescopes and refined methods, we will gain deeper insights into the intricate history of our universe and the stars that inhabit it. Ultraluminous X-ray sources, commonly referred to as ULX, are extraordinary astrophysical phenomena found in various galaxies beyond our own. They are characterized by their incredibly high X-ray luminosities, exceeding 1 million times that of the Sun. ULXs are of great interest to astronomers because they represent some of the most intense X-ray emissions observed in the universe, producing radiation that often surpasses that generated by typical stellar sources. The exact nature of ULXs remains a subject of active research, but they are generally believed to be associated with binary systems involving a compact object, such as a black hole or neutron star, that is accreting matter from a companion star. In particular, many ULX are thought to house black holes in the mass range of a few to several tens of solar masses, which distinguishes them from stellar mass black holes typically found in our galaxy. The accretion process occurs when matter from the companion star flows onto the black hole, generating immense amounts of energy as the infalling material heats up and emits X-rays. Another intriguing possibility is that some ULX could be associated with intermediate mass black holes, which are a missing class of black holes believed to have masses between 100 and 1,000 solar masses. Finding these intermediate mass black holes in ULXs could shed light on the formation of supermassive black holes found in the centers of galaxies, which can have masses millions or even billions of times that of the Sun. Moreover, ULXs may also exhibit variability in their brightness, indicating they undergo changes in their accretion rates. Sudden flares and fluctuations can provide further insight into the dynamics between the accreting material and the compact object. This variability often makes ULXs a rich field for studying the fundamental physics of black holes, accretion flows, and the environments in which they exist. The study of ultraluminous X-ray sources continues to evolve, driven by advances in observational technology and observational campaigns in both optical and X-ray wavelengths. As we learn more about these enigmatic objects, they offer a unique window into extreme astrophysical processes and the interplay between stars and their compact remnants, enriching our understanding of the cosmic landscape. Each discovery adds another layer to the intricate tapestry of the universe and fuels the quest to comprehend the fundamental nature of matter and energy in extreme environments. The phenomenon of some galaxies exhibiting little to no star formation despite having abundant gas is a captivating area of research in astrophysics. At first glance, it seems counterintuitive. Having copious amounts of gas, which is the primary fuel for star formation, should lead to active stellar birth. However, various factors can inhibit the process, leading to a state known as star formation quenching. One significant reason for this quenching is linked to the dynamics within the galaxy itself. In certain cases, the gas in these galaxies may not be sufficiently dense or cool enough to collapse into stars. Factors such as turbulence or heating from existing stars can prevent the gas from cooling and condensing, creating a barrier to star formation. For example, in some massive elliptical galaxies, the presence of supermassive black holes at their centers can drive powerful winds or jets that heat the interstellar medium, effectively slowing down or halting the cooling processes necessary for star formation. Moreover, galaxy mergers and interactions can profoundly impact star formation rates. When galaxies collide, they can funnel gas towards their centers, triggering bursts of activity. But in other instances, these interactions can result in the gas being expelled from the galaxy or redistributed in ways that inhibit star formation. The gravitational forces at play can strip gas away or create conditions that stabilize the gas against collapse into stars. Another contributing factor can be the role of dark matter and the overall gravitational potential well of the galaxy. For galaxies that are not actively forming stars, the binding energy of the dark matter halo may not provide the conditions needed to retain gas effectively. Gas stripping, either from interactions with the surrounding environment or from the effects of a larger gravitational potential within a galaxy cluster, can also lead to the removal of gas that would otherwise be available for star formation. Additionally, the cosmic web's role cannot be overlooked. The large-scale structure of the universe influences the flow and distribution of gas. In some regions, the inflow of gas from the intergalactic medium may be suppressed due to the large-scale environment, further limiting the amount of gas available for star formation. Understanding why certain galaxies can maintain significant quantities of gas without converting it into stars adds critical insight into galaxy evolution. As researchers delve deeper into this topic using advanced observational techniques and simulations, they strive to uncover the intricate interplay of gravitational, hydrodynamic, and chemical processes that shape the lives of galaxies throughout cosmic history. Each new finding deepens our understanding of galaxy formation and evolution, revealing the complex nature of the universe we inhabit. The ripples observed in the disk of the Milky Way are fascinating phenomena that provide insights into the dynamics of our galaxy. These ripples are primarily caused by gravitational interactions among stars within the disk, as well as the influence of nearby structures. One significant contributing factor is the passage of spiral arms. When stars and gas clouds move through these arms, they experience gravitational pulls that create disturbances, leading to wave-like patterns in the distribution of stars and gas. Additionally, interactions with satellite galaxies play a crucial role in creating these ripples. The Milky Way is not an isolated entity. It has several small galaxies orbiting it, such as the large and small Magellanic Clouds. The gravitational pull from these neighboring galaxies can induce tidal forces that affect the star distribution in the Milky Way's disk. Over astronomical time, these interactions can build up and create observable waves or ripples in the galaxy's structure. Another interesting aspect is the potential involvement of dark matter. While we cannot see dark matter, it's believed to make up a significant portion of the galaxy's mass. Its gravitational influence can also contribute to the motion of stars, leading to the formation of these rippled patterns. This concept allows scientists to study the effects of dark matter indirectly through the behavior of visible stars. As researchers continue to analyze data from telescopes and other instruments, they unravel the complexities of the Milky Way's structure. Understanding these ripples not only helps us comprehend our own galaxy, but also sheds light on the interactions that occur in other galaxies throughout the universe. Each ripple tells a story of cosmic motion and the gravitational dance between celestial bodies. The intricate and symmetrical shapes of some planetary nebulae arise from a complex interplay of processes during the late stages of a star's life. When a medium-sized star, similar to our Sun, exhausts its nuclear fuel, it undergoes a series of transformations. As the core contracts and heats up, the outer layers of the star are expelled into space, forming a glowing shell of gas and dust known as a planetary nebula. The symmetry often observed in these nebulae can be attributed to the dynamics of this ejection process. One of the primary factors influencing the shape is the role of magnetic fields. As the star sheds its outer layers, the magnetic fields can create organized structures within the expelled material. These fields help guide the flow of gas, leading to more uniform, intricate shapes rather than random distributions. In many cases, these magnetic fields also interact with the stellar wind, the stream of charged particles ejected from the star, enhancing this ordered structure. Additionally, binary star systems contribute significantly to the formation of symmetrical shapes. If a star exists in a binary system, interactions between the two stars can lead to mass exchange and the shaping of the ejected material. One star may shed its outer layers while the companion's gravity pulls and directs this material, creating a more structured and recognizable form. This gravitational interaction can lead to the formation of jets and lobes that give rise to the unique and often beautiful shapes that we observe. The combination of these processes produces the breathtaking patterns seen in planetary nebulae, which can range from round and spherical to more complex forms, including intricate knots and filaments. The study of these structures not only enhances our understanding of stellar evolution, but also provides clues about the physical conditions in the later stages of a star's life. Each planetary nebula is a snapshot of cosmic processes and showcases the artistry of nature in the universe. The interstellar object known as Oumuamua has intrigued scientists since its discovery in 2017, presenting a unique opportunity to study a visitor from outside our solar system. Oumuamua is believed to be of rocky or metallic composition, and its unusual shape is elongated and cigar-like, which is quite different from typical asteroids or comets found within our solar system. The name Oumuamua comes from Hawaiian, meaning scout or messenger, aptly reflecting its status as the first detected interstellar object to pass through our planetary neighborhood. Scientists speculate that Oumuamua originated from a star system outside our own, having been ejected from its home galaxy. This ejection could have been driven by gravitational interactions with other stars, which might have caused it to be cast away at high speeds. Once liberated from its original star system, Oumuamua traveled for millions of years through the vastness of space, eventually finding its way to the inner solar system, where we detected it. Another intriguing aspect of Oumuamua's journey is its trajectory. The object displayed unusual acceleration as it traveled through the solar system, which some scientists initially attributed to outgassing, a common feature observed in comets. However, the lack of a visible comet-like tail led researchers to consider alternative explanations, including the possibility that it is a fragment of a larger body or perhaps plays a role in the complex dance of interstellar dynamics. Ultimately, Oumuamua serves as both a scientific enigma and a reminder of the dynamic nature of the cosmos. Its presence raises fundamental questions about the distribution of interstellar objects and the processes that govern their movement through space. With ongoing research and observations, scientists hope to learn more about the origins and properties of such visitors, paving the way for a deeper understanding of the universe beyond our own solar system. The presence of multiple populations of stars with differing compositions in some star clusters offers a compelling glimpse into the complex history of these celestial formations. In particular, this phenomenon is most noticeable in globular clusters, ancient groups of stars that orbit galaxies. The distinct populations can be traced back to the environment in which the clusters formed and the subsequent evolutionary processes they underwent. One of the primary reasons for these multiple populations is the initial conditions present during the cluster's formation. Many star clusters formed in dense regions of gas and dust, where the first generation of stars created heavy elements through nuclear fusion processes. Once these stars reached the end of their life cycles, they enriched the surrounding material with these heavier elements, known as metallicity. This enriched gas later became the raw material for the next generation of stars, leading to the creation of a second population with a different composition, often showcasing higher metallicity than the first. Furthermore, interactions among the stars within the cluster can contribute to the diversity in stellar populations. As stars evolve, some can shed material, which may be accreted by younger stars, further altering their chemical compositions. In addition, it is theorized that some clusters experienced periods of star formation that were spaced out over millions of years. These intervals allowed for differing compositions to emerge as the stellar environment evolved. Moreover, in some cases, the discovery of multiple populations challenges previous understandings of how star clusters evolve. The idea that globular clusters may have formed from the merging of smaller clusters suggests that what we find today is a blend of different star-forming events sharing space within the gravitational hold of the cluster. This complex interplay of formation history and stellar evolution makes studying these star clusters particularly fascinating, as they unveil the processes that shape the universe on a grand scale. Each cluster contains a wealth of information about the life cycle of stars and the chemical evolution of galaxies. The periodic brightening of the blazar OJ 287 is a remarkable phenomenon that has captivated astronomers for decades. Blazars are a class of active galactic nuclei characterized by their powerful jets of relativistic particles pointing nearly directly toward Earth. These jets emit radiation across the electromagnetic spectrum, and OJ 287 is particularly notable for its brightness variation, which occurs roughly every 12-year cycle. The periodic activity observed in OJ 287 is attributed to the interaction of a supermassive black hole at the center of the galaxy with another black hole. This system consists of a primary black hole that is actively accreting material surrounded by a secondary black hole in a binary system. As the companion black hole orbits the larger one, it produces gravitational effects on the material in the accretion disk surrounding the main black hole. These gravitational influences can enhance the accretion process, leading to increased radiation output when the companion black hole gets closer. During the periods of heightened activity, the energy released as the material spirals into the black hole increases significantly. This surge causes the blazar to brighten dramatically, producing the observable outbursts that we detect from Earth. The mechanism of these outbursts can also include the complex interactions of shock waves traveling down the jet, further amplifying the brightness through the Doppler effect, as the material moves close to the speed of light. The cyclical nature of OJ 287 reinforces the understanding of black hole interactions in active galactic nuclei. Observations of its brightening not only provide insights into the behavior of matter under extreme conditions, but also help improve our knowledge of the dynamics involved in such massive systems. OJ-287 serves as a vital source of information in the broader quest to comprehend the workings of the universe at its most energetic and fundamental levels. Binary systems often undergo a phase known as common envelope evolution, which can significantly alter their structures. This occurs when one of the stars in the binary expands into a giant star, enveloping the other star in a shared outer layer of gas. The gravitational interaction between the two stars can lead to a dramatic transformation of their orbits and can potentially result in the ejection of the outer envelope. However, some binary systems manage to survive the common envelope phase, and this resilience can be attributed to several key factors. One important factor is the relationship between the masses of the two stars involved. If the secondary star is sufficiently massive, it can help stabilize the common envelope phase by retaining some of the material ejected from the primary star. This retention may ultimately allow the two stars to continue interacting, promoting additional mass transfer and enabling them to remain bound to one another. The interaction of the secondary star also helps in dissipating energy, which can prevent the envelope from becoming too diffuse, allowing the binary system to evolve successfully. Additionally, the dynamics of the common envelope itself play a significant role in the outcome. During this phase, the stars can undergo dramatic changes, including a rapid decrease in orbital separation. If the energy released from the infall of the primary star's envelope into the companion's core is sufficient to expel the common envelope entirely, the evolutionary path can lead to a tighter binary configuration. This tighter orbit may result in the two stars becoming closer together, enhancing their interaction rates and setting the stage for future evolution. The presence of additional factors, such as the spin and the rotation of the stars, can also impact the binary system's ability to navigate through common envelope evolution. The orientation of the stars' spins and their magnetic fields may influence the physics of the envelope dynamics, thereby affecting whether the binary system can survive or not. In cases where the stars are aligned favorably, this interplay can help the system maintain its integrity and prevent it from completely breaking apart. These mechanisms demonstrate that binary systems are capable of diverse evolutionary pathways, allowing them to adapt and survive even after undergoing intense transformations. Understanding how these systems manage such transitions provides insights into the complex life cycles of stars and the intricate relationships that can form in the cosmos. Each binary system offers a unique narrative about stellar evolution and the diverse outcomes that can arise from the interactions of massive objects in space. The James Webb Space Telescope represents a groundbreaking advancement in our quest to understand the early universe. Equipped with a suite of advanced instruments and a large mirror, Webb is designed to capture infrared light, which allows it to peer deeper into space and time than any previous telescope. This capability makes it uniquely suited to study the first galaxies that formed after the Big Bang and to observe the conditions that set the stage for the universe as we know it. One of the key features of Webb is its ability to observe distant celestial objects that emit their light at wavelengths longer than visible light. As galaxies move away from us due to the expansion of the universe, their light shifts toward the red end of the spectrum, a phenomenon known as redshift. By focusing on these longer wavelengths, Webb can detect the faint light from the earliest galaxies, which formed roughly 400 to 800 million years after the Big Bang. This will allow astronomers to examine the formation and evolution of these early cosmic structures in unprecedented detail. Webb is also poised to provide new insights into the formation of stars and planetary systems. Its sensitivity to infrared radiation enables it to study dense regions of gas and dust where stars are born, revealing processes that were previously hidden from view. By observing stellar nurseries and examining the chemical composition of the materials present, scientists will gain a better understanding of how the elements necessary for life formed in the early universe and how stars and planets evolved over time. Furthermore, as Webb explores exoplanets and their atmospheres, it will allow researchers to assess the habitability of these distant worlds. The telescope can analyze the chemical signatures of exoplanet atmospheres, searching for the presence of molecules like water vapor, carbon dioxide, and potentially even ozone. By expanding our knowledge of which environments could support life beyond Earth, Webb will contribute significantly to our understanding of the universe's potential for hosting life. The James Webb Space Telescope represents a monumental leap in our capabilities for cosmic exploration. It will illuminate the dark epochs of the universe's history, revealing both the vastness of time and the intricate processes that shaped galaxies, stars, and potentially life itself. Its discoveries have the potential to challenge existing theories and inspire new questions, fundamentally enhancing our grasp of the cosmos. Gravitational wave astronomy is an exciting new field that has already transformed our understanding of the universe since the first detection of gravitational waves in 2015. As the technology continues to evolve and more advanced detectors come online, we can anticipate several breakthroughs in the coming decades that will deepen our knowledge of astrophysical phenomena and offer new insights into fundamental physics. One major area of discovery will be the study of black hole mergers. As more gravitational wave events are detected, astronomers expect to gather invaluable data about the properties and population of black holes in the universe. This includes determining their masses and spins, as well as the rates at which these massive objects collide and merge. Understanding these dynamics may shed light on the formation mechanisms of black holes and their role in the evolution of galaxies. It could also lead to insights into the nature of extreme gravity and the fundamental laws governing black hole physics. Another significant potential breakthrough lies in the observation of neutron star mergers. Gravitational waves produced by these events carry crucial information about the ultra-dense matter comprising neutron stars. By analyzing the gravitational wave signals in conjunction with electromagnetic observations, scientists can gain insights into phenomena such as the formation of heavy elements in the universe through processes like kilonova explosions. This multi-messenger approach, combining gravitational waves and electromagnetic signals, promises to enhance our understanding of cosmic events and the synthesis of elements. Gravitational wave astronomy also has the potential to probe fundamental physics beyond our current theories. For instance, studying the behavior of gravitational waves could help address questions about the nature of dark matter and dark energy. Furthermore, researchers are exploring the possibility of using gravitational waves to test the linearity of general relativity, leading to a deeper understanding of gravitational forces themselves. These explorations could pave the way for advanced theories that may unite general relativity with quantum mechanics, addressing long-standing questions in physics. Lastly, the advent of future gravitational wave observatories, such as the European Space Agency's LISA mission and other proposed projects, will allow for the detection of lower-frequency gravitational waves. These observations could uncover new types of astrophysical events, such as the mergers of supermassive black holes at the centers of galaxies and potential signals from primordial gravitational waves that were produced during the early moments of the universe. Overall, the next decades in gravitational wave astronomy hold the promise of revolutionizing our understanding of the universe, unraveling mysteries of its most enigmatic and extreme phenomena. Neutrino astronomy holds the potential to revolutionize our understanding of the universe by offering unique insights into cosmic phenomena that are otherwise difficult to study through traditional electromagnetic observations. Neutrinos are subatomic particles that interact very weakly with matter, allowing them to travel vast distances through the universe without being absorbed or deflected by intervening material. This characteristic makes them valuable messengers from some of the most extreme environments in the cosmos. One of the most significant applications of neutrino astronomy is in studying high-energy astrophysical sources, such as supernovae, active galactic nuclei, and gamma-ray bursts. These cosmic events generate a vast number of neutrinos during their explosive or energetic processes. For instance, when a massive star collapses, it releases an immense flux of neutrinos that can provide critical information about the physical conditions during the explosion. By detecting these neutrinos, scientists can gain insights into the mechanisms driving these violent events and further our understanding of stellar evolution. Additionally, neutrino astronomy can enhance our comprehension of cosmic rays, which are high-energy particles originating from various astrophysical sources. Some of these cosmic rays are believed to be accelerated in supernova remnants, active galaxies, or even colliding neutron stars. As cosmic rays interact with matter, they can produce neutrinos. By studying the neutrinos that result from these interactions, researchers can trace the origins of cosmic rays back to their sources and learn about the conditions present in those extreme environments. Moreover, neutrinos could also provide valuable information about the processes occurring in the early universe. They are believed to have played a crucial role in the dynamics of the early universe shortly after the Big Bang. Observing the relic neutrinos from that epoch, often referred to as cosmic neutrino background radiation, could offer clues about the universe's evolution, the formation of structures, and the mechanisms behind inflation. As neutrino detection technology advances, the field of neutrino astronomy will continue to grow, revealing insights from the most elusive and energetic processes in the universe. By complementing electromagnetic observations from telescopes that capture light across various wavelengths, neutrino astronomy creates a more comprehensive view of the cosmos. This combination of different observational techniques will allow scientists to build a richer understanding of the fundamental processes that govern both the celestial objects and the universe at large. Future missions to the ice giants, Uranus and Neptune, promise to unveil significant insights into their unique characteristics, atmospheres, and the broader dynamics of our solar system. Despite being part of our solar neighborhood, both planets remain underexplored and hold a wealth of scientific questions that have yet to be answered. A dedicated mission aimed at these enigmatic worlds could significantly enhance our understanding of planetary formation and evolution. One of the primary areas of interest is the atmospheric composition and weather patterns of Uranus and Neptune. Both planets exhibit dynamic atmospheres with striking features such as storms, winds, and even potential seasonal changes. By studying their atmospheres in detail, future missions could provide critical data about the processes that drive these phenomena. Understanding their composition, particularly the presence of gases like methane, ammonia, and water, could shed light on how ice giants formed and the role they played in the early solar system. Another important aspect of these missions would be the study of the internal structures of Uranus and Neptune. Understanding the internal dynamics, such as whether they possess layered atmospheres, rocky cores, or even oceanic components, is essential for developing comprehensive models of their formation. This knowledge can help researchers compare these ice giants with gas giants like Jupiter and Saturn, revealing the diversity of planetary types in our solar system and offering insights into exoplanets found around distant stars. Additionally, exploring the magnetic fields and magnetospheres of Uranus and Neptune presents an opportunity to understand their unique magnetic environments. Unlike other planets in our solar system, these ice giants have tilted and offset magnetic fields that do not align with their rotational axes. Investigating these magnetic characteristics may provide valuable insights into the interiors of these planets and the complex processes occurring deep within them. Future missions to Uranus and Neptune could also hold keys to understanding the history and evolution of the solar system itself. By studying these planets, scientists hope to gain insights into the formation conditions of ice giants and their migration patterns during the solar system's infancy. Furthermore, as researchers continue to discover exoplanets similar to Uranus and Neptune, the knowledge gained from studying our own ice giants will serve as a comparative basis for better understanding these distant worlds. Missions to Uranus and Neptune are poised to enhance our understanding of the solar system's diversity, planetary dynamics, and the formation of planetary systems, making them essential targets for future exploration. Each new discovery could reshape our perspectives on planetary science and inspire further research into the mysteries of our cosmic neighborhood. Advanced artificial intelligence and machine learning are poised to revolutionize the analysis of astronomical data, fundamentally changing how scientists explore and interpret the cosmos. The sheer volume of data generated by modern telescopes and observatories is staggering, often reaching petabytes from surveys of the night sky. Traditional methods of analysis can struggle to keep pace, But AI offers tools that can efficiently process and extract meaningful information from this data flood. One major improvement lies in the ability of machine learning algorithms to identify and classify celestial objects automatically. Given the vast array of phenomena detectable in the universe, ranging from stars and galaxies to transient events like supernovae and gamma-ray bursts, developing automated systems that can classify these objects quickly and accurately is crucial. By training models on labeled datasets, researchers can create powerful classifiers that can recognize patterns that might remain undetected through traditional methods, thereby enabling astronomers to focus on the most promising leads for further investigation. Additionally, AI can be instrumental in addressing the challenges of signal detection among noise and background interference. For instance, when searching for gravitational waves or exoplanets, distinguishing genuine signals from random noise is essential. Machine learning algorithms can be employed to sift through data and highlight anomalies, improving the chances of discovering new phenomena. In cases where faint signals may be masked by larger noise levels, these algorithms can enhance sensitivity, allowing scientists to uncover subtle features that may indicate novel astrophysical events. Another promising application is in the realm of simulation and forecasting. AI can help model complex astrophysical processes, such as galaxy formation or stellar evolution, by analyzing large datasets from simulations. These models can assist researchers in making predictions about the behavior of celestial objects and phenomena, thereby refining our understanding of the underlying physical processes at play. Through iterative learning, these models can evolve, improving their accuracy over time and adapting to new datasets. Moreover, as multi-wavelength observations become increasingly common, integrating data from various sources can be challenging. Machine learning provides tools for data fusion that can synthesize information from optical, infrared, radio, and other wavelengths, leading to a more comprehensive understanding of celestial phenomena. This capability is particularly valuable for studying complex systems, such as active galactic nuclei or the interplay of different components within a galaxy. The potential of AI and machine learning in astronomy is vast and continues to expand. As these technologies evolve, they will enable researchers to process, analyze, and interpret astronomical data with unprecedented efficiency and accuracy. This transformation will not only facilitate the discovery of new astronomical phenomena, but also enhance our understanding of the universe's fundamental principles, opening new frontiers in cosmic exploration. Future large-scale galaxy surveys hold the promise of providing transformative insights into our understanding of the universe. These extensive observational campaigns are designed to map billions of galaxies across vast regions of space, collecting a wealth of data on their properties, distributions, and interactions. The information gathered from these surveys will enable researchers to address fundamental questions about the cosmos while refining existing theories of galaxy formation and evolution. One of the significant areas of exploration will be the large-scale structure of the universe. By studying the distribution of galaxies, astronomers can analyze the cosmic web, the intricate network of filaments and voids that shapes the universe on the largest scales. Understanding how galaxies are grouped and spread out offers essential insights into the evolution of structures since the Big Bang. These studies can also provide data on dark matter and dark energy by revealing how these unseen components affect the motion and clustering of galaxies across vast distances. Another important focus will be investigating the properties and characteristics of different galaxy types. Large-scale surveys will allow scientists to classify galaxies based on various criteria such as their morphology, star formation rates, and chemical compositions. By correlating this data with environmental factors, researchers can gain a better understanding of how galaxies evolve in different cosmic environments, such as isolated regions versus denser clusters. This knowledge can help us piece together the mechanisms that drive galaxy evolution and formation, particularly during critical periods in their life cycles. The surveys will also facilitate the study of galaxy dynamics and interactions. Many galaxies exist in close proximity to one another, and their gravitational interactions can lead to significant changes in their structures and star formation activity. By observing how galaxies collide and merge, researchers can learn more about the processes that lead to the growth of supermassive black holes at their centers and the resulting impact on their host galaxies. This knowledge will deepen our understanding of the physics governing galaxy evolution. Lastly, large-scale galaxy surveys will enhance the search for exoplanets and habitable environments beyond our solar system. By investigating the stellar populations within galaxies and their distribution across cosmic time, astronomers can identify which types of stars and planetary systems are most likely to support life. The information gleaned from these surveys will be crucial in understanding the broader question of life in the universe. The insights gained from future large-scale galaxy surveys will have far-reaching implications, deepening our understanding of the universe's structure, the processes driving galaxy evolution, and the search for life beyond Earth. As these surveys progress, they will undoubtedly benefit from advancements in technology and data analysis, enabling a more comprehensive exploration of the cosmos and refining our place within it. Detecting and studying primordial gravitational waves presents an exciting frontier in cosmology, as these waves carry insights from the universe's earliest moments, particularly from the period of cosmic inflation just after the Big Bang. To uncover primordial gravitational waves, researchers are focusing on several advanced techniques and technologies that aim to isolate these elusive signals from the background noise of the universe. One of the most promising approaches involves using highly sensitive cosmic microwave background, or CMB, observations. Primordial gravitational waves are expected to leave a specific imprint on the CMB, the afterglow radiation from the Big Bang. When gravitational waves ripple through the fabric of spacetime, they can influence the polarization of the CMB. By measuring this polarization, scientists can search for distinctive signatures that would indicate the presence of primordial waves. Ongoing and upcoming missions, such as the upcoming advancements in compact interferometers and those involving ground-based telescopes like the Simons Observatory, are focused on precisely mapping the polarization patterns in the CMB to improve sensitivity for such detections. Another promising avenue for detection is through the use of advanced gravitational wave observatories. Projects like the Laser Interferometer Space Antenna, or LISA, aim to detect gravitational waves in lower frequencies, which may include signals from the merging of supermassive black holes formed from the early universe. Although their direct evidence might differ from the primordial gravitational waves from inflation, these observations could help paint a broader picture of the gravitational landscape in the early cosmos. If LISA can confirm or detect these lower frequency waves, it will significantly advance our understanding of gravitational wave propagation and their early inception. In addition, upcoming terrestrial detectors like the next generation of the Laser Interferometer Gravitational Wave Observatory, known as the Einstein Telescope, will have enhanced sensitivity at higher frequencies, making these detectors more capable of discerning gravitational waves potentially originating from cosmic events linked to the early universe. By correlating findings from different detectors operating at various frequency bands, scientists can explore a wider range of gravitational sources. Finally, researchers are also exploring the potential of new theoretical models and simulations to predict the characteristics of primordial gravitational waves, which may guide observational strategies. By improving our understanding of how these waves interact with matter and energy in the universe, scientists can enhance the design of detection instruments and refine their search algorithms. Through a combination of innovative observational techniques and advanced gravitational wave detector technology, the quest to detect and study primordial gravitational waves will continue to evolve. Success in this endeavor could deepen our understanding of cosmic inflation, the conditions that shaped the early universe, and fundamentally refine our understanding of the nature of space-time itself. Each discovery will provide cosmic breadcrumbs that can lead to a more comprehensive understanding of the universe's origin and evolution. A future interstellar probe sent to nearby star systems could profoundly enhance our understanding of the cosmos, particularly in terms of the formation of planetary systems, the potential for extraterrestrial life, and the overall dynamics of stellar environments. With advancements in technology and propulsion methods, such a probe could provide direct data from beyond our solar system, offering insights that are currently speculative or based purely on remote observations. One of the primary goals of an interstellar probe would be to study the planetary systems around neighboring stars, such as Proxima Centauri, Alpha Centauri A, and Alpha Centauri B. By analyzing the compositions, atmospheres, and potential habitability of exoplanets in these systems, researchers could significantly expand our understanding of how planets form and evolve. The probe could assess the presence of water, organic molecules, and other essential elements necessary for life, contributing to the search for extraterrestrial life and examining if similar conditions to those on Earth can arise in other parts of the galaxy. Additionally, a probe could investigate the stellar environment, including solar activity and magnetic fields, which directly influence the planets orbiting those stars. Understanding how stellar winds and radiation impact planetary atmospheres can provide crucial context for assessing habitability and potential biosignatures. For instance, learning how different stars may affect the atmospheres of their orbiting planets would offer valuable data on the habitability of those systems and how they may differ from our own. Moreover, studying the interstellar medium, the tenuous gas and dust between the stars, would be another significant benefit of sending a probe beyond our solar system. As the probe travels, it could analyze particle composition, magnetic fields, and radiation levels, contributing to our knowledge of the physical conditions in interstellar space. This information could help scientists better understand the processes that drive the evolution of galaxies and star systems over time. In addition to these scientific inquiries, an interstellar probe could serve as a crucial stepping stone for future exploration. By collecting data on the challenges of traveling through interstellar space, such as radiation exposure, navigation, and power requirements, engineers and scientists could refine technologies necessary for longer human-crewed missions beyond our solar system. Finally, sending a probe beyond our solar system focuses not only on celestial science but also deeply engages the public imagination. The very act of exploring the stars can inspire a new generation of scientists and enthusiasts, fostering a renewed interest in space exploration and the search for life beyond Earth. A future interstellar probe has the potential to unlock a wealth of knowledge about the nature of nearby star systems, the conditions for life, and the dynamics of our galaxy. Each discovery will bring us one step closer to answering some of the most profound questions about our place in the universe and the existence of life beyond Earth. Detecting and studying the cosmic neutrino background represents a bold and challenging frontier in astrophysics. Primordial neutrinos, produced during the first moments of the universe, provide valuable information about the conditions and processes occurring shortly after the Big Bang. These relic neutrinos could shed light on the early universe's temperature, density fluctuations, and the formation of large-scale structures. However, their detection is particularly difficult due to their weak interaction with matter. One promising approach to detect the cosmic neutrino background involves using large-scale neutrino detectors. These facilities consist of vast volumes of material that can capture the rare interactions of neutrinos. Detectors like IceCube at the South Pole or proposed next-generation detectors such as the SBN, Short Baseline Neutrino Program, aim to be sensitive enough to identify low-energy neutrino interactions. Researchers are focused on developing more advanced detector technologies, such as liquid argon or water-based systems, that can enhance the sensitivity to lower-energy neutrino signals expected from the cosmic neutrino background. Another potential method to study these primordial neutrinos is through their effects on cosmic microwave background, or CMB radiation. The presence of primordial neutrinos influences the dynamics of the universe during its early stages, imprinted in the CMB's temperature fluctuations. By analyzing the detailed maps of the CMB, scientists can look for signatures that suggest the existence of the neutrino background. Ongoing and planned missions investigating the CMB, such as the Atacama Cosmology Telescope and future satellite missions, may provide crucial data that supports or refines theoretical models that include the effects of cosmic neutrinos. Moreover, advancements in astrophysical simulations will play a vital role in guiding experiments and observations. By modeling the behavior of cosmic neutrinos and understanding their impact on other particles and fields in the early universe, astronomers can better identify where to focus their efforts in searching for direct signatures. These simulations can also help predict the expected energy spectrum and distribution of the relic neutrinos, which informs the design of detection strategies and instruments. Finally, collaborative efforts across multiple scientific disciplines are crucial for successfully detecting and studying the cosmic neutrino background. By combining data from neutrino detectors, CMB observations, and cosmological surveys, scientists can build a more comprehensive picture of the conditions in the early universe. Such multidisciplinary approaches will enhance our understanding of fundamental physics and the processes that shape the cosmos. In conclusion, while detecting the cosmic neutrino background remains a formidable challenge, innovative technologies and collaborative research efforts are paving the way for potential breakthroughs. Success in this endeavor could unlock new insights into the origins and evolution of the universe, further illuminating the fundamental forces at play and how they intertwine to shape the cosmic landscape. Future space-based telescopes are poised to unravel numerous mysteries within our solar system, capitalizing on advancements in technology and observational techniques. These telescopes, equipped with state-of-the-art instruments, will enable researchers to investigate celestial bodies with unprecedented detail and sensitivity, leading to potential breakthroughs in our understanding of the solar system's formation, evolution, and current dynamics. One of the primary areas of exploration will be the study of distant objects in the Kuiper belt and the Oort cloud, which are remnants from the early solar system. Space-based telescopes can provide detailed observations of these icy bodies, such as Pluto and its fellow dwarf planets, allowing scientists to analyze their compositions, surface features, and atmospheres. Understanding the chemical and physical properties of these objects will help piece together the history of the solar system and the processes that shaped planetary formation. For instance, discoveries related to the presence of organic molecules or evidence of past geological activity could rewrite our understanding of the conditions prevalent during the solar system's infancy. Additionally, space-based telescopes will enhance our ability to monitor and study comets and asteroids, which are crucial for understanding the building blocks of the solar system. Observing these bodies in detail can reveal insights into their interiors, surface processes, and how they interacted with other solar system objects. By studying their orbits and properties, researchers may also assess the risk of potentially hazardous asteroids, which is vital for planetary defense. Another exciting avenue of exploration is the search for signs of life or habitability on the moons of gas giants and icy worlds like Europa, Enceladus, and Titan, and future telescopes could analyze the plumes of water vapor ejected from these moons, searching for biosignatures or other indicators of biological activity. The ability to study these environments from space will contribute to our understanding of whether conditions suitable for life exist beyond Earth. Furthermore, space-based telescopes will provide crucial datasets for investigating solar phenomena and their interactions with planetary atmospheres. By studying solar activity and its impact on planets, researchers can gain insights into the effects of solar wind on planetary magnetospheres and atmospheres. This understanding is important not only for planets like Mars, where solar wind played a significant role in atmospheric loss, but also for understanding climate processes on Earth and other worlds. Ultimately, the combination of detailed imaging, spectroscopy, and the ability to observe across multiple wavelengths will empower future space-based telescopes to uncover an array of solar system mysteries. Each discovery will contribute to a more comprehensive understanding of the dynamics at play in our cosmic neighborhood, enlightening the processes that govern the formation and evolution of planetary systems. The continued exploration of our solar system promises to reveal its many secrets and foster an appreciation for the vastness and complexity of the universe we inhabit.